What if the universe wasn't just around you, but inside you? What if the silence you hear isn't silence at all, but a storm hidden behind your senses? Imagine learning that the laws of physics you were taught in school only scratch the surface. That, beneath reality, lies a deeper code, one that rewrites time, space, memory, and even your identity. That the constants we take for granted, like mass, light, and gravity, are mysterious placeholders for forces we barely understand. Over the next 4 hours, we'll descend into the gaps of known science, where time might not be real, space might not be empty, and your thoughts might not be yours alone. This isn't science fiction. It's the uncomfortable edge of physics, consciousness, and the nature of existence. So if you're ready to dismantle what you think is real, if you're ready to question every law you've ever trusted, tap like, hit subscribe, and follow me into the unseen machinery of the universe. Why time flows only forward. Physics allows reversibility, yet time doesn't. What if I told you the most unstoppable force in your life, the one you chase, resist, waste, and beg for more of, doesn't even exist the way you think it does? That time, which feels like a river pulling you from birth to death in one irreversible direction, is in fact a riddle in physics, an illusion shaped by perception, not an arrow etched into the universe. You wake up every morning older than yesterday. You see broken glass on the floor and instinctively know it was once whole. A baby becomes a child becomes a memory. This flow of time feels absolute, relentless. But dig into the mathematics of the universe, the very laws that govern motion, energy, particles, and something eerie emerges. Those laws don't care about forward or backward. They are time symmetric. In theory, they work just as well in reverse. A movie of two atoms colliding looks just as valid played backwards. The equations are blind to direction, and yet, your life is not. You remember the past but not the future. You grow older, never younger. Ice melts, but never unmelts. Why? Why does time have a direction in your experience if the fundamental laws of physics say it doesn't? This paradox, this rupture between physical symmetry and human experience, has haunted science for over a century. To explain it, physicists point to entropy, a measure of disorder. According to the second law of thermodynamics, entropy always increases in a closed system. It's why your coffee cools instead of heating up, why rooms get messy instead of spontaneously cleaning themselves, why death is irreversible. Entropy gives time a direction. It's the cosmic one-way sign painted on the universe. But entropy itself doesn't cause time to move forward. It's a statistical pattern, a likelihood, a gradient from order to chaos. So the question deepens: why did the universe start in a state of such low entropy that it allowed for this increase in the first place? Why wasn't it born already in equilibrium, in perfect chaos, where time has no arrow and no meaning? Some physicists speculate that the Big Bang set the initial conditions, that our universe began like a perfectly stacked deck of cards, destined to shuffle itself into disorder over billions of years. But that only pushes the mystery further back. Why did the deck start so ordered? And this leads us to another unsettling realization. Your brain, your memories, your consciousness is wired to record entropy. You don't remember yesterday because it's in the past. You remember it because it left an imprint, a trace, a measurable change. You saw things, felt things, encoded neural patterns that altered your internal state. That change is entropy. The future hasn't left its mark yet, so you can't recall it. In this sense, time is not a flow. It's a contrast between memory and prediction, between imprint and possibility. You are a biological thermodynamic system, navigating a world that appears to change because your internal entropy keeps increasing. Your perception of time is not a window to the universe. It's a side effect of being made of matter, governed by heat and decay. You feel time moving forward because that's the only direction in which entropy can increase for you. And if your brain was somehow capable of running backwards, if it could reverse every chemical process, every synapse, every memory, you would experience time in reverse and still believe it was flowing forward. That's how deep the illusion goes. Still, the rabbit hole gets deeper, because entropy doesn't explain everything. In the world of quantum mechanics, time behaves even stranger. Certain quantum processes do break time symmetry, creating what's called time asymmetry. Some particles decay in a way that shows a preference for one direction of time, but these exceptions are rare and tiny, and not enough to explain why your entire existence moves forward like a film that can't be rewound. Others propose that time itself is not fundamental, that it's not part of the deep structure of the universe at all. Theoretical physicists working on quantum gravity and loop theory suggest that time may emerge from more fundamental timeless laws, just as temperature emerges from the chaotic dance of atoms. In this view, time isn't real. It's a statistical average, a convenient illusion your brain uses to make sense of change. Imagine a symphony with no tempo, no beat, just overlapping chords and melodies. Time is the rhythm you impose to hear a coherent song. Reality is the symphony. You are the metronome. So what do we do with this knowledge? Does it change anything about the heartbreak of aging, the tragedy of loss, the beauty of memories? Maybe it does. Maybe it reminds you that the present isn't slipping away. It's being recorded, transformed into patterns of entropy and experience that will one day become the architecture of your past. Maybe it frees you from the panic of time's passing. Because if time is not a river, but a construct, a frame we paint around motion, then perhaps there's more freedom than we thought. Maybe now is just a spotlight, and you get to choose where to aim it. Maybe you don't need to fear the future, because in some sense, it already exists in another part of the block universe, another still frame in the cosmic film reel. And maybe that gives weight to the choices you make. Not because time is running out, but because every moment you live becomes part of an eternal pattern, a slice of a timeless whole. And still, something in you resists this, something deep. And human says, no, I feel time. I watch my child grow. I see the seasons turn. I wake up older each morning. You can't tell me that's not real. And you're right, it is real, but it's not fundamental. It's a byproduct of your position in the universe, of your brain's need for coherence, of entropy's quiet pull through the corridors of existence. The arrow of time is not written into the stars. It's whispered into your nervous system. It is felt, not dictated. You are not a prisoner of time. You are its translator, its storyteller, its witness. So the next time you stare at a sunset and feel the ache of something slipping away, remember, it's not the universe letting go of you. It's your brain telling you a story, a beautiful, heartbreaking, necessary story about what it means to change, about what it means to be alive in a world that pretends to move forward, even though the laws beneath it say otherwise. And maybe that's the final gift of time's illusion, not to show us what's real, but to remind us what matters. What enforces the Pauli exclusion principle? We use it, but can't explain it. Some rules of the universe are shouted. Gravity pulls, light travels, energy transforms. But others are whispered, hidden in silence, woven into the invisible script that lets everything exist without collapsing into itself. One of those rules is so vital that without it, stars wouldn't shine, atoms wouldn't hold their shape, and the chair you're sitting on would dissolve into quantum dust. It's called the Pauli exclusion principle, and it's the quiet law behind structure itself. It tells us that no two fermions, particles like electrons, protons, or neutrons, can occupy the exact same quantum state. In other words, no two electrons in an atom can be in the same place, with the same energy, spinning in the same way. It's a simple phrase, easy to memorize. But here's the mystery. Why? Why does the universe enforce this rule so relentlessly, so precisely, that the very matter of your body depends on it? What power tells particles, you may not be the same? What agency draws that line in the quantum sand? And why can no one cross it? Physics can tell you how the rule plays out. It can describe the mathematical landscape where electrons fill energy levels like tenants in a building, each floor uniquely assigned. But ask what enforces the rule, what actually prevents a particle from defying it, and you're met with a kind of shrug. It just doesn't happen. Not because there's a visible barrier, not because there's a measurable force, but because reality has decided, somehow, that this configuration is off limits. And the strangest part, it's not even a force in the traditional sense. There's no push, no pull, no field resisting overlap. The exclusion is absolute, but silent, like a cosmic etiquette so ingrained, no one even considers breaking it. It's as if the universe itself remembers that uniqueness matters, and enforces that memory without ever needing to raise its voice. Imagine a room full of people where no two are allowed to wear the same color, speak in the same tone, or stand in the same pose. Not because someone is watching or threatening punishment, but because existence itself unravels if even one rule is broken. That's what atoms are like. Each electron must carve its own identity, unique orbit, unique spin, unique state. Not because it wants to, but because there is no alternative. If they tried to be the same, they wouldn't just overlap. They would cease to be. It's a law with no enforcer, and yet it's never violated. That's what makes the Pauli exclusion principle so eerie, so haunting. It's not just a physical limitation, it's a metaphysical boundary, a built-in no baked into the fabric of being. And yet, we use it every day without thinking. The solidity of matter, that's the Pauli exclusion principle in action. When you press your hand against a wall, you don't fall through, not because atoms physically touch, because they don't, but because the electrons in your hand and the electrons in the wall refuse to share space. Not out of stubbornness, but out of law. Their quantum states repel overlap, not through electrical force, but through identity itself. And this has staggering implications. It means that everything solid, everything separate, everything structured in your world is made possible by an abstract principle that offers no force field, no visible mechanism, only constraint by definition. The exclusion principle gives rise to the periodic table, to chemical behavior, to the existence of white dwarf stars whose collapse is halted not by heat or magnetism, but by degeneracy pressure. A resistance born purely from the refusal of electrons to crowd into sameness. When a massive star dies, and gravity tries to squeeze it into oblivion, it's this invisible rule that pushes back. A rule without mass, without energy, just a principle. It's like the entire universe depends on a sacred "you shall not pass" echoing in every atom. And yet we don't know why it works. The equations tell us that fermions obey the antisymmetric wave function. Swap two of them and the wave flips. Sign, cancelling out if they're the same. Bosons, like photons, do the opposite. They love to be in the same state, stacking together like social creatures in a crowded room. That's why light can amplify, why lasers can exist. But fermions, they isolate, they differentiate, they stake their claim and hold it. Mathematically, this distinction arises from something called spin statistics theorem. But the theorem doesn't explain why, it describes. Like so much of quantum mechanics, it tells us what happens, not why it must be so. It is a curtain, not a stage. It shows you the shape of the rule, but never its source. And this opens the door to something deeper. What if the exclusion principle isn't just a rule of physics, but a message? A reflection of some deeper order that prioritizes uniqueness, identity, boundaries. In a cosmos where so much seems chaotic, the Pauli exclusion principle is the quiet reminder that identity matters, that nothing, no particle, no person, no pattern can fully duplicate another. There will always be some variation, some distinction, some sliver of space reserved for uniqueness. It's not just a physical necessity, it's a philosophical one. It's the reason complexity exists, the reason we have diversity, structure, emergence, the reason you are not me and I am not you. And so we're left with a mystery. One we can measure, rely on, build computers and skyscrapers and quantum theories upon, but not fully understand. A rule that has never been broken, yet offers no reason for its authority. It is one of the rarest things in science, a principle that works perfectly, but lives without explanation. And maybe that's why it resonates so deeply, because in a world full of questions, there's something beautiful about an answer that stands firm, not because we understand it, but because reality itself refuses to disobey. The Pauli exclusion principle isn't just a constraint, it's the whisper that keeps the universe from becoming a featureless blur. It's the breath between the notes. The reason the symphony doesn't collapse into a single tone. It's the invisible signature on every structure, the law behind individuality. And maybe, just maybe, it's the universe's way of saying, there's room for everything, but not if everything tries to be the same. Why is mathematics so unreasonably effective in describing reality? Imagine writing a poem in a language you never learned, only to discover that every word you scribbled perfectly describes the ocean, the sky, the movement of planets, and the growth pattern of leaves. That's what mathematics feels like. A silent script etched into reality, discovered, not invented by human minds, yet somehow always one step ahead of our understanding. It's as if we're decoding a message left, not by a god, but by existence itself. Why does math, abstract, sterile, emotionless, fit the universe with such haunting precision? Why do numbers born in chalk-dusted classrooms end up predicting black holes, chemical reactions, the orbits of moons, and the structure of your DNA? This isn't just convenient, it's eerie, unnatural almost. It suggests a connection between thought and reality so deep that it brushes the edges of mysticism. But the question remains, why? Why is math not just a tool, but a mirror? Why do we find equations not only useful, but prophetic? At first glance, you might assume it's coincidence, that we shape math to match what we observe, like carving, a key to fit the lock we already built. But that doesn't explain how formulas dreamed up with no application in mind, pure mathematical curiosities, end up perfectly describing physical phenomena decades or centuries later. Complex numbers were once abstract nonsense. Now they're the foundation of quantum mechanics. Riemannian geometry, created for beauty, became the backbone of Einstein's theory of general relativity. Differential equations, once esoteric puzzles, now model pandemics, stock markets, and neural networks. It's as if mathematics knows something we don't. Like it's not just a language we speak, but one we're slowly remembering. Some physicists believe math is the ultimate compression algorithm, the universe's way of being lazy, using the smallest set of rules to generate the richest complexity. Others think it's a byproduct of our brains, useful but not fundamental. But if that were true, why does it work on scales and in realms we've never evolved to perceive? Why can we describe galaxies we'll never touch using symbols etched on paper? Maybe it's not math that's unreasonable. Maybe it's our surprise that's unreasonable. Maybe the universe is built not on matter or energy or even information, but on pattern. And math is the name we give to patterns precise enough to touch. But even that doesn't quite answer it, because math isn't just accurate, it's beautifully accurate. It doesn't just work, it sings. Equations like Euler's identity don't just describe reality, they whisper something deeper. That the universe isn't chaos, but choreography. That the stars don't stumble, they waltz. That particles don't collide, they perform. Math reveals the rhythm beneath randomness, the structure beneath change. It's the music sheet beneath the universe's symphony. And somehow, we keep finding the notes before we hear the song. There's no reason the square root of 1 should help us describe quantum entanglement, but it does. There's no reason prime numbers should underpin encryption and chaos theory, but they do. Over and over, math doesn't just describe, it predicts. And that predictive power makes it feel less like a tool and more like a law. Not something we use to understand the world, but something the world obeys. This brings us to a philosophical fork in the road. One path says that math is simply how our brains model the world. It works because we made it to work. But this can't explain why math that no one designed for nature ends up describing nature. The other path says that math is woven into the fabric of reality, that it is discovered, not invented, that we're not creating models of the universe, we're peeling away its skin. This is the Platonic view, that mathematical truths exist independently of us, and we stumble across them like explorers finding ancient ruins in the forest. In this view, reality isn't physical, it's mathematical. You aren't made of atoms, you're made of information, of geometry, of equations, dancing in flesh. This is the idea behind the mathematical universe hypothesis, that physical reality is not the foundation, but the output. That the cosmos is not a machine running math, it is math running itself. And what if that's true? What if the deepest reality isn't what we see, or touch, or measure, but the math beneath it all? Would that make the universe more meaningful? Or more alien, more intimate, or more indifferent? Maybe it depends on how you feel about numbers, about beauty, about truth. Because in math, we find something rare, something that doesn't change with culture, or time, or emotion. A universal constant, a shared language not just across continents, but across galaxies. And perhaps that's what makes its effectiveness feel so unreasonable. Not because it's spooky, but because it's intimate. Because it suggests that the universe and the human mind are not separate domains, but two branches of the same tree, reaching in different directions, built on the same root. So the next time you solve a simple equation, or marvel at the spiral of a sunflower, or watch waves form perfect sine curves across the ocean, pause. Ask yourself, why does this work? Why does the abstract match the real? Why do the shapes in your notebook know how the stars move? There may be no final answer, but the question alone reveals something sacred, that we are not strangers in this universe. We are part of its grammar. We are the question mark scribbled into its margin. And math is the punctuation that reminds us there's a sentence here, long, strange, beautiful, and that somehow we're still learning how to read it. Do particles truly exist? Or are they just vibrations in fields? What if everything you think is solid, permanent, or real is nothing more than a ripple in something invisible? What if the smallest pieces of you, the protons in your blood, the electrons in your fingertips, the quarks spinning quietly in your DNA, aren't really things at all, but disturbances, not objects with boundaries, but fleeting events, tremors in an unseen ocean that spans the entire universe? You've been taught that the world is made of particles, that beneath your skin and bone lies a zoo of subatomic building blocks, electrons, photons, quarks, neutrinos, tiny marbles zipping through the void. But modern physics whispers a more unsettling story, one that replaces particles with patterns, one that says there is no thingness, only activity, as if reality itself is a kind of music, and everything you know is just a note being played. Welcome to the mystery of quantum fields, a theory that doesn't just change what we know, it rewrites what it means to exist. To understand how strange this is, imagine a calm pond stretching out in every direction. Now toss a pebble. Waves ripple outward, brief, beautiful, and entirely made of the water they disturb. Those ripples aren't objects, they're behaviors, localized tremors in a broader, more stable fabric. Now stretch that metaphor across the entire universe. Replace the pond with a field, not water, but a kind of invisible presence that fills all space, even the emptiest vacuum. These fields don't flow, they don't move like liquids, but they are everywhere. Every type of particle, electrons, quarks, photons, has its own field, omnipresent and silent. And what we call a particle is just a tiny excitation in that field. A ripple, a vibration, a blip in the matrix of space-time. The electron you think of as a tiny bead orbiting an atom. It's actually a tiny shiver in the electron field. The photon carrying light from a distant star to your eyes. just a flicker in the electromagnetic field. You don't see the fields, you only see their disturbances, their notes, their echoes. This is what physicists call quantum field theory, QFT, arguably the most accurate and successful framework we've ever built. It describes not a world of objects flying around in space, but a world of overlapping, interwoven fields, each capable of momentarily vibrating into what we perceive as particles. When you see an atom, you're not seeing tiny billiard balls stuck together. You're witnessing a choreography of resonances, like sound waves harmonizing into a stable chord. Reality isn't made of particles at all. It's made of excitations. And this changes everything, because if particles are just temporary blips, then they don't exist in the way we typically understand existence. They don't have sharp boundaries. They don't persist. They come into being, flicker, interfere, and fade. They're not things, they're events. But this revelation opens a deeper, more existential question. If particles aren't real in the classical sense, then what is? If all matter is just field activity, then you too are a bundle of overlapping vibrations. Your thoughts, your memories, your sense of self, all arising from a storm of fields echoing in unison. You are not a thing. You are a pattern, a convergence of resonances held together by temporary harmony. And that's not poetry. That's physics. The fields themselves don't blink in and out. They are continuous, eternal, unchanging in their presence. It's their local disruptions that come and go, like waves forming and fading on a vast cosmic ocean. In this view, you are a standing wave, a long-lasting but ultimately temporary reverberation in an unimaginably deep field system. And that realization either terrifies you or frees you. But how do we know this is true? Because QFT doesn't just work, it predicts things with godlike precision. The magnetic moment of the electron, predicted and measured to match across 12 decimal places, the interactions between light and matter, described flawlessly by quantum electrodynamics, a child of QFT. Particle accelerators like the Large Hadron Collider smash energy into fields and produce particles, not from hidden marbles, but from the raw vacuum, proving that matter can emerge from pure field excitation. When we detected the Higgs boson, it wasn't a new particle added to a zoo. It was a ripple in a field we had theorized decades earlier. The Higgs field doesn't just exist, it gives existence. Without it, particles wouldn't have mass. You wouldn't be here. Mass is not an attribute. It's a result, a consequence of interaction between ripples and the ever-present Higgs field. And that may be the strangest part of all. Even something as solid as mass is just another echo. So where does this leave our understanding of stuff? What is the chair you're sitting on, if not a collection of atoms? It's a structured orchestra of field vibrations, stabilized into long-term harmony. The illusion of solidity comes not from actual physical contact, because particles don't really touch, but from the exclusion principles and electromagnetic forces that emerge from fields behaving in specific, mathematically beautiful ways. The chair is real, yes, but not as a thing, as a song, as a recurring melody in the language of fields. Even space itself isn't truly empty. The vacuum is not a void. It's seething, teeming, with field fluctuations, quantum foam, virtual, particles that pop in and out of momentary being. This nothingness has properties. It can exert pressure, create force, affect particles. In fact, the so-called Casimir effect proves that even two uncharged plates placed in a vacuum will attract, not because of anything between them, but because of the quantum fluctuations of the vacuum itself. Nothing isn't nothing. It's everything, waiting to vibrate. And this brings us to the philosophical edge. If particles are just localized field vibrations, and if those fields are everywhere, then the entire universe is more like a single, continuous dynamic fabric than a scattered collection of independent things. It means separation is an illusion. It means the electron in your fingertip is part of a field that spans Alpha Centauri. It means that the boundaries between self and world, object and void, are conceptual conveniences, not fundamental truths. Fields don't begin or end, they are entire. You don't live in the universe, you are a ripple of the universe. And that ripple thinks, and doubts, and loves, and asks questions like this. So do particles truly exist? Not in the way we imagined. There are no tiny marbles, no hard-edged building blocks, only happenings, only temporary resonances in eternal fields. We named them particles because we needed something to point at, something to count. But what we found, the deeper we looked, were patterns too graceful for such crude labels. The universe isn't made of things, it's made of activity. It dances instead of sits. It pulses instead of persists. And you, beautiful, impermanent, conscious ripple that you are not separate from this dance. You are part of the rhythm. So the next time you look at your hand, or at the stars, or at someone you love, remember, you are not observing a world made of parts. You are witnessing a harmony of invisible vibrations, a symphony of fields rising and falling like breath. Particles do not sit, they sing, and the universe listens. The fine structure constant, a number that controls the universe without explanation. Some numbers you encounter in life are arbitrary: phone numbers, locker codes, street addresses. They have meaning only because we assign it. But some numbers seem baked into reality itself, not chosen, not constructed, discovered. Numbers that don't just describe the universe, but govern it. One of those numbers is so mysterious, so fundamental, so eerily precise that physicists have called it a magic number, a fingerprint of God, and the most important number in physics. It has no units, no obvious reason, and no known derivation, yet everything from the structure of atoms to the behavior of light depends on it. That number is the fine structure constant, and it might just be the universe's most cryptic signature. It shows up everywhere, explains so much, and yet no one knows why it has the value it does. And if it were even slightly different, you wouldn't be here to wonder about it. Let's start with what it is. The fine structure constant is a dimensionless number, meaning it's pure. It doesn't depend on meters or seconds or kilograms. It's just itself. Its approximate value is 1137, that's it, one number, but encoded within it is the strength of the electromagnetic force, the interaction that holds atoms together, governs chemistry, and lets your eyes receive light. Without this constant, electrons wouldn't orbit nuclei in stable paths. Photons wouldn't scatter correctly. Stars wouldn't shine in the same way. Life, as we know it, would be impossible. But more than that, it's not just that this number is essential, it's that we have no idea where it comes from. It doesn't fall out of theory. It doesn't emerge from deeper logic. It's just there, sitting in the equations like a riddle written in permanent ink. To understand its power, imagine trying to compose a universe. You have to balance forces. Too strong, and atoms collapse. Too weak, and they never form. You need just the right tension between attraction and repulsion, just the right nudge to let light and matter interact, but not so much that they annihilate each other. The fine structure constant controls this balance. It's the dial on the cosmic mixing board that determines how light and matter speak. And what's wild is how often it appears. Quantum electrodynamics. It's there. Atomic spectra. There. The probability that an electron will emit or absorb a photon. There. Even the way electrons split into subtly different energy levels, fine structures as they're called, is controlled by this one number. It's not just in the math, it's in the texture of reality. But here's the thing. In physics, we like explanations. We're comforted by cause. We want to derive, to deduce, to reduce things to first principles. But the fine structure constant resists this. We measure it, we use it, we confirm it to incredible accuracy, but we don't explain it. We don't know why it's 1137 and not 1138 or 112 or 42, and we don't even know if it could have been otherwise. Maybe it's necessary. Maybe it's arbitrary. Maybe there's an infinite landscape of universes, each with a different value, and we live in the one where the number just happens to support life. That's the anthropic principle. The idea that the universe is the way it is, because otherwise we wouldn't be here to notice. But that doesn't satisfy. It doesn't feel like an answer. It feels like a shrug. Some theories try to connect the fine structure constant to deeper mathematical structures. String theory hints that it may emerge from the geometry of curled-up dimensions. Other frameworks suggest that it could change over time, that the constant might not be constant at all. There have even been astronomical observations hinting at tiny variations in its value across space. If true, that would shake physics to its core, because a universe where constants can shift is a universe with fluid laws, a cosmos still writing itself rather than obeying a fixed script. But so far, the data remains inconclusive. So we're left with this number, this 1137, carved into the laws of nature with no visible author. And it gets stranger. The number 137 has fascinated not only physicists, but mystics, numerologists, and spiritual thinkers. Why? Because it's pure. No units, no context, just truth. Theoretical physicist Wolfgang Pauli, one of the pioneers of quantum mechanics, was obsessed with 137. He believed that understanding it might unlock a door not just in physics but in reality itself. Legend has it, he died in a hospital room numbered 137. Mere coincidence, or a poetic echo of a lifelong quest? Of course, we must be cautious not to romanticize. Numbers have power, but they are not gods. Still, the fine structure constant feels like a clue, a message, a whisper in the equations saying, there's more, keep looking. And maybe that's its greatest gift, not what it explains, but what it refuses to explain. It humbles us, reminds us that even as we master the atom and map the cosmos, there are still doors we can't open, still truths we don't own, still mysteries that sit silently in the math, waiting. So what happens if this number changes? Just a bit. Say, instead of 137, it were 136. The consequences ripple across everything. Electrons orbit differently, chemistry breaks down. Stars might not fuse hydrogen. Life, if it arises at all, might look nothing like us, or never arise at all. The universe is balanced on this number like a tightrope walker over an abyss. One slip, one decimal point off, and everything collapses. That fragility, that precise fragility, suggests intentionality, or design, or perhaps a terrifying randomness that looks like design. And in that ambiguity lives the tension of modern physics. We can describe the universe down to breathtaking detail, but we still don't know why it works. And maybe we never will. Maybe the fine structure constant is one of those eternal mysteries. Not because it's beyond reason, but because it is reason. A kind of foundational truth that defies simplification. Like the axioms of geometry, it doesn't come from anything. It is the ground we build from. And if that's true, then the universe isn't a story written in particles or waves, but in numbers. And the fine structure constant is not just a number, it's the pulse of reality, the silent tempo that all matter dances to. So the next time you turn on a light, or touch a hand, or look at a star, pause. Know that what you're experiencing is only possible because a number you've never seen, never questioned, never truly understood, is exactly what it is. That beneath your every thought, every molecule, every beam of light, there lives a mystery too elegant to be an accident and too silent to be ignored. It doesn't shout, it doesn't change. It just waits, forever embedded in the code of the cosmos, asking us not to solve it, but to listen. The cosmological constant problem. Why is vacuum energy so small yet so powerful? You probably imagine emptiness as peaceful, a quiet, still nothingness, a void, a place where nothing exists, and therefore nothing happens. But what if I told you that nothingness is a lie? That the most barren vacuum imaginable is, in fact, roaring with power? That the fabric of empty space is not calm, but convulsing, seething with energy? What if the thing we call nothing turns out to be the most mysterious something in all of physics? At the heart of this paradox lies the cosmological constant problem, a problem so profound that physicists have called it the worst prediction in the history of science. Because what we calculate and what we observe differ not by a little, but by a factor of 10^120. That's a number so vast, it exceeds the number of atoms in the universe. And yet, both sides of this impossible equation, both the emptiness of the vacuum and the relentless expansion of the cosmos, are real. They're not philosophical thought experiments. They're measurable, observable, undeniable. And that's what makes the cosmological constant problem not just a scientific riddle, but a window into the fundamental structure of reality. To grasp it, we have to start with a concept that sounds simple but isn't: vacuum energy. According to quantum field theory, even empty space is not truly empty. It's filled with quantum fields, those strange, invisible presences that span the universe and occasionally flicker into what we call particles. Even when these fields are in their lowest possible state, no particles, no heat, no light, they still vibrate. They still have energy. This is the zero-point energy of the vacuum. It's like the universe can never sit perfectly still. Even when stripped of everything, space hums. And when you add up the contributions from all known fields, all possible frequencies, the expected vacuum energy becomes enormous, catastrophically enormous. So large, in fact, that it should have warped space-time beyond recognition. Stars wouldn't exist. Galaxies wouldn't form. The universe would either collapse immediately or rip itself apart in a fraction of a second. But that's not what we see. Instead, we see a universe that's expanding, not chaotically, but slowly, steadily. The expansion itself was discovered a century ago, but what shocked cosmologists in the late 1990s was that the expansion is accelerating. Galaxies are not just moving apart, they're being pushed apart faster and faster over time. Some hidden pressure, seems to be stretching space-time itself. And this pressure acts exactly like the repulsive effect of vacuum energy. Einstein first introduced the cosmological constant into his equations to allow a static universe, then called it his greatest blunder when the universe turned out to be expanding. But now, it seems he was right to include it, just wrong about why. Because this constant, this little term added to balance gravity, seems to describe the very thing we now call dark energy, a force that pushes outward, driving the expansion of the cosmos. And here's the paradox. We observe this force. We can calculate its strength from how fast distant galaxies accelerate away. And when we do, we find a number, a cosmological constant, that is tiny, minuscule, barely there. But when we calculate vacuum energy from quantum theory, we get a number that is incomprehensibly large. The two values differ by 120 orders of magnitude. To put that into perspective, it's like predicting the height of a person should be larger than the entire observable universe, and then finding that it's actually smaller than a virus. The discrepancy is not just big, it's unthinkable. It implies that either our understanding of quantum fields is wildly flawed, or some as yet unknown mechanism, is cancelling out almost all of the vacuum energy, leaving behind just a whisper, a residue, just enough to stretch the universe, but not enough to tear it apart. This is what makes the cosmological constant problem so devastating. It's not a minor inconsistency, it's a fracture in our foundation. Quantum field theory works incredibly well at small scales. General relativity works spectacularly at large ones. But when we ask them to talk about the vacuum, where quantum fluctuations curve space-time, we get nonsense. It's as if two master composers wrote separate symphonies that each sound perfect on their own, but when you play them together, they explode in your ears. And yet, the vacuum exists. The expansion exists. The cosmological constant exists, so what's wrong? Some physicists propose supersymmetry, a beautiful theory where every particle has a heavier partner and their energy contributions cancel each other out. But we haven't found those particles. Others suggest that we're only seeing a slice of a multiverse, and in other universes, the cosmological constant is different. Ours just happens to be in the Goldilocks zone where life can evolve. But that's not an explanation. It's a selection effect. It replaces a mechanism with an accident. It says there's no deeper reason. You just live in a lucky bubble. But physicists aren't satisfied with luck. They want laws. They want understanding. And that's what makes this problem so haunting. It's not that we don't know the answer. It's that we don't even know what kind of answer to look for. And in the meantime, the vacuum keeps pushing. Every second, every moment, it stretches space just a little bit more. This is dark energy, the name we give to something we do not understand. It makes up 68% of the energy content of the universe. Think about that. Nearly 3/4 of the cosmos is something we can't see, can't touch, and can't explain. We don't know what it is. We only know what it does. It accelerates the expansion, quietly, relentlessly. It's not a burst. It's a whisper, a pressure that never stops, a constant tension in the fabric of reality that keeps stretching and stretching. And the implications are profound. Because if dark energy continues, if the cosmological constant remains constant, then the universe will not just expand. It will end in isolation. Galaxies will drift so far apart that their light will never reach each other again. Stars will die, new ones won't form, matter itself may decay, and the cosmos will become cold, dark, and empty. Not because something destroyed it, but because something emptied it. A slow erasure, not by violence, but by distance. A universe undone by the very vacuum it emerged from. So what do we do with this knowledge? We live in a cosmos ruled not by what's visible, but by what's hidden. The most powerful force in existence might be the energy of nothing, and that should terrify us, or humble us, or both. Because we thought emptiness was simple. We thought space was a stage, not a character. But now we know that the void is not silent. It speaks. And what it says is this: I am not nothing, I am everything. And so the cosmological constant remains, not just a number, but a question. A paradox carved into the bones of the universe. A riddle with no punchline. A force that shapes the future while hiding its origin. And maybe, just maybe, that's what makes it so beautiful. Because some mysteries don't need solving to be worth exploring. Some truths are not for grasping, but for marveling. And in the silent breath of the vacuum, in the quiet push that moves galaxies like leaves on an unseen wind, we find a whisper of that mystery. Ever present, ever small, ever vast. Are physical constants actually constant across the universe? What if the laws that govern reality were not laws at all, but local guidelines, rules that apply only in our small cosmic neighborhood, like the customs of a town unaware that the world beyond its borders operates differently? We've long trusted that the universe follows a unified script, that the speed of light, the strength of gravity, and the charges of particles are immutable truths, constants written into the very fabric of space and time. These are the numbers we build our theories upon, the scaffolding that holds up our physics and our sense of predictability. But what if that trust is misplaced? What if those constants are more like suggestions, firm in our region of the cosmos, but variable elsewhere? What if the rules of existence are not universal at all? It's a question that threatens to unravel everything we know. Because if the constants aren't constant, then the laws derived from them, laws we consider foundational, begin to crack. Imagine baking a cake with a recipe that says, bake at 350 degrees, only to discover that your oven reads temperatures differently than every other oven in the world. or that the concept of 350 degrees varies from kitchen to kitchen. That's the magnitude of the crisis we'd face if constants like the fine structure constant, gravitational constant, or Planck's constant turn out to be regional rather than universal. It would mean that reality as we experience it is not reality as it truly is. It's a regional dialect of physics, not its native language. Let's pause on that fine structure constant, often represented by the Greek letter alpha, A. It's an odd creature, a dimensionless number, approximately 1/137, that appears everywhere in quantum electrodynamics. It defines the strength of the electromagnetic force, how atoms hold together, how light interacts with matter. Richard Feynman once called it one of the greatest damn mysteries of physics, asking why this number exists, why it has the value it does, and whether it has always been that way. Because if alpha varied, just a little, then the entire architecture of matter would shift. Chemistry as we know it wouldn't work. Stars might not form. Life might never arise. But what makes this idea more than a philosophical itch is that we've started to look for evidence. Light from distant quasars has become a kind of time capsule, carrying the fingerprints of ancient atoms through billions of years of cosmic expansion. By analyzing the absorption lines in the spectra of that light, scientists can probe how alpha might have behaved when the universe was young. And here's the unsettling part. Some of those studies suggest slight differences in the constants, a value across time and space. Not all the data agrees. This is not a closed case, but even the possibility whispers something profound, that the universe might be more of a patchwork than a monolith. It doesn't stop with alpha. What about the gravitational constant G? It's the number that tells you how strongly masses attract each other. It governs the dance of planets, the formation of galaxies, the curvature of space-time itself. And yet, our measurements of G have historically been inconsistent, not by much, by fractions of a percent, but enough to raise eyebrows. Could this be due to measurement error, or is it a hint that gravity might not be a single unchanging force, but one that fluctuates across the vast reaches of the cosmos? If these constants are not fixed, then what sets them? Are they governed by deeper laws, perhaps hidden dimensions, or as yet undiscovered fields? Some theories, like string theory or certain versions of the multiverse hypothesis, suggest that the values of physical constants may depend on the configuration of extra dimensions or the vacuum state of the universe itself. In other words, there could be countless pocket universes, each with its own set of constants, its own version of reality. We just happen to live in one where the constants are what they are, not because they must be, but because they can be. This leads to a disturbing possibility that the physical laws we revere are not fundamental at all, but emergent properties of our local patch of the multiverse. It's as if we were ants living on a scrap of fabric, unaware that the weave changes elsewhere. We've spent centuries building a science that assumes uniformity, test here, predict there. But if the constants shift, even subtly, then our predictive power falters the moment we look too far beyond. The cosmos stops being a unified code and becomes a quilt stitched from incompatible patterns. Of course, not everyone agrees. The majority of physicists still operate under the assumption that constants are constant, and with good reason. All repeatable experiments done on Earth, all local astronomical observations, show remarkable consistency. GPS satellites rely on these constants to work, and they do, reliably, precisely. The standard model of particle physics, our best description of the subatomic world, would collapse if the constants were not stable. Yet the very precision of these systems becomes a trap. We mistake reliability for universality. But the real question isn't whether we can trust the constants here, it's whether we can trust them everywhere, because the universe is vast beyond comprehension, and the data we have barely scratches the surface. We're like travelers who've mapped a few islands and declared the entire ocean charted. The very fact that we're asking this question is a sign of how far we've come and how far we have yet to go. There's something deeply human in this uncertainty. We crave stability, predictability, constants in our relationships, in our beliefs, in our universe. To be told that the most fundamental quantities in existence might be unstable is to be reminded again of how fragile our knowledge really is. And yet this fragility is not a weakness. It is a kind of beauty, the beauty of a mind that keeps questioning, even when the answers are unsettling. So where does this leave us? At the edge of a mystery. The constants may be constant, or they may not. But the act of questioning them opens the door to deeper understanding. It reminds us that science is not a monument to certainty, but a lighthouse built in the storm of the unknown. The light it casts helps us navigate, even as the ocean of truth remains wild and unmapped. And perhaps that's the ultimate constant, not the speed of light or Planck's constant, but our capacity to wonder. As long as we keep asking, as long as we remain curious, the universe will continue to reveal itself, piece by piece, mystery by mystery. Why inertia exists. Mass resists motion, but physics can't say why. Imagine you're in a car parked on a quiet road. You press your foot on the gas pedal, and for a moment, just a blink, the car hesitates. Then it lurches forward. You feel it in your chest. That small jolt as your body resists the change. The same thing happens when the car suddenly stops. Your torso wants to keep going even though the brakes have brought the machine to a halt. This stubbornness, this strange resistance to motion or to stillness, is something so deeply embedded in our everyday lives that we rarely question it. It just is. A force we feel in roller coasters and collisions, in spinning merry-go-rounds and sudden stops. But if you peel back the layers of our physics textbooks, behind Newton's laws and Einstein's space-time, behind equations and predictions, you find something eerie. No one actually knows why it happens. We call it inertia. The tendency of a mass to resist changes in its motion. And we use it constantly, in calculations, in design, in engineering, in theory. But behind the certainty of its presence lies a gaping philosophical and scientific mystery. Why does mass resist acceleration at all? Why does the universe behave as if it abhors sudden movement? You can tell me how to measure it, you can describe how it manifests, but you cannot explain why it exists, and that should make you pause. It's easy to take it for granted. After all, Newton enshrined inertia as the first of his laws. Objects in motion stay in motion, objects at rest stay at rest, unless acted upon by a force. But Newton didn't explain it, he merely described it. He noticed its behavior, gave it a name, and moved on. Centuries later, Einstein added layers of geometric beauty through general relativity, but even he didn't answer the core question. It was assumed, not understood. Like gravity before Newton saw the apple fall, inertia is something we live with but cannot truly see through. It's a ghost in the machine of physics, obvious in effect, elusive in origin. Let's think of it differently. Imagine the universe as a giant dance floor. Every particle is a dancer. Some stand still, some glide gracefully in motion. Inertia is the mysterious resistance that pulls at each dancer when they try to switch steps. It's not friction. There's no visible rope pulling back. It's an invisible reluctance, embedded not in the floor, not in the shoes, but within the very identity of the dancers themselves. Why? One possible thread to follow leads us into the dense fog of quantum field theory. In this view, particles are not standalone entities, but disturbances in vast, invisible fields that stretch across space and time. A photon is a ripple in the electromagnetic field. A Higgs boson is a ripple in the Higgs field. In this ocean of invisible presence, mass isn't something an object has. It's something an object experiences. The Higgs field, specifically, is said to give mass to fundamental particles via interaction. Some glide through it easily, like electrons. Others slog, like top quarks. But this still doesn't tell us why that mass resists motion. Why should interaction with a field imply a refusal to accelerate? The math works, But the intuition doesn't click. The explanation is partial, functional, but not foundational. And what if inertia is not a property of matter alone, but a kind of silent conversation with the rest of the universe? This is where Ernst Mach enters the stage, a 19th century physicist whose ideas inspired Einstein. Mach proposed that inertia might be the result of an object's interaction with all the mass in the universe. That when you push a chair, its resistance comes not just from itself, but from its gravitational conversation with every galaxy, star, and planet that exists. It's as if, in trying to move anything, you're subtly tugging on the entire cosmos, and the cosmos pushes back. This idea, though poetic, remains unproven, but it touches something deep. The sense that inertia is not just a local property, but a global phenomenon, a handshake between the particle and the universe. And if that's true, then inertia is not just unexplained, it's profound. It speaks to an unseen unity, a whisper of connectedness between all things. And yet we use it daily in physics as if it's fully understood. We simulate planetary orbits, launch rockets, design bridges and airplanes, and they all work. The formulas behave, the predictions come true. But beneath that surface lies a question mark as bold as any in science. Why does mass push back against change? Why does the universe resist spontaneity in movement? It is here, in the silent refusal of objects to suddenly leap forward, that we encounter a kind of metaphysical gravity. A reminder that not all truths are answers. Some are mysteries we live inside. Inertia becomes a metaphor for human nature itself, the way we cling to comfort zones, how we resist sudden changes in our lives, how we long for motion but fear acceleration. Perhaps our very psychology echoes this cosmic principle. We are creatures of inertia, emotional, intellectual, and physical. So what do we do with this mystery? We acknowledge it. We stop pretending it's solved. We marvel at the strangeness of a universe where the most basic experiences, a shove, a start, a stop, hide the deepest unknowns. And we remember that progress in science does not come only from answers, but from the courage to sit with questions. Inertia, in this light, is not merely a phenomenon. It's an invitation. An invitation to stop assuming we understand what we've merely learned to describe. An invitation to wonder why the universe has texture at all, why it resists, why it pushes back, why it cares about motion. And maybe that's the real answer we're after. Not a formula, not a mechanism, but a deeper appreciation that the universe is not a machine, it's a conversation, and inertia is one of its oldest replies. Why the electron's mass is what it is, no known reason. What if I told you that one of the most fundamental properties in the entire universe, the very trait that makes electricity work, atoms stay intact, chemistry happen, and matter exist, as we know it, comes from a number we don't understand at all, that the electron, that tiny, almost weightless particle zipping around atoms, owes its mass not to some elegant equation or universal law, but instead to a value that just is? Not because we've derived it, not because nature explained it, but because, for reasons unknown, the universe whispered it into existence and left us with no clue why. Imagine baking a cake and one ingredient, say sugar, determines the flavor of the entire world. But when you ask why this sugar, why this amount, why this taste, all you get is silence. That's the mystery of the electron's mass. It's like someone handed us a cosmic recipe with the word because scribbled next to the most important measurement. This number, roughly 9.109 times 10 to the negative 31 kilograms, seems small, laughably so, yet its impact echoes across the fabric of everything you've ever touched, seen, or known. But here's the strange part. We have no deeper answer for where it comes from, no satisfying explanation for why it's not twice as much, or half. Why not zero? Why not infinity? Why is the electron's mass so perfectly tuned that if it were even slightly different, the stars wouldn't burn, atoms wouldn't bond, and life as we know it would collapse into chaos. And yet, this crucial value, this cosmic dial set just so, emerged from the early universe with a quiet certainty, as if written into the code of reality itself, without footnotes or documentation. The standard model of particle physics, for all its success in describing interactions and forces, offers no real insight into why the electron has the mass it does. Yes, it links mass to the Higgs field, the invisible ocean that permeates space and gives mass to particles through interaction. But the Higgs mechanism only tells us how particles acquire mass, not why each one has this specific amount. It's like knowing how paint sticks to a canvas, but having no idea why someone chose these exact colors. The electron's mass isn't derived from first principles. It's input, an assumption, a placeholder, a value we measure with precision, use with confidence, and yet cannot explain. That makes it not just a mystery, but a paradox, because science thrives on reasons, on connections, on asking why, and getting something more than just because that's how it is. But in the case of the electron's mass, we hit a wall, a fundamental gap between knowing and understanding. And it should terrify us a little, because if we don't know why the electron weighs what it does, what else don't we know about the architecture of existence? If we were to tweak this one number just slightly, would our entire understanding of reality unravel like a thread from a tightly woven tapestry? Some physicists have dared to explore deeper. Theories like supersymmetry attempt to relate the masses of different particles, hoping to find a hidden order beneath the apparent randomness. String theory imagines particles as vibrating loops of energy, where mass might arise from tension and geometry in extra dimensions. But these remain speculative frameworks, not confirmations, elegant castles in the fog. Meanwhile, the observable truth remains fixed. The electron has mass. It is not massless like the photon, nor crushingly heavy like the top quark. It sits somewhere in the lower range, light enough to dance through atoms, heavy enough to have an identity. And that placement is key. Change it even slightly, and chemistry breaks down. The bonds that hold molecules together become unstable. Carbon no longer forms. DNA doesn't twist. The spark of life flickers out before it can begin. That is the power of a number we didn't choose. The mass of the electron is like the tension on a violin string, so precisely tuned that even a minor adjustment throws the entire orchestra into dissonance. And yet the violinist, the force or field or process that chose this mass, remains hidden behind the curtain, unnamed, unseen, and maybe not even real. Maybe the electron's mass isn't chosen at all. Maybe it's an accident, a result of symmetry, breaking in the early universe. Maybe it's one of many values in a multiverse of possibilities, and we just happen to live in the version where this particular number allows for complexity, consciousness, and curiosity. If that's true, then physics becomes less like a search for truth and more like reading a survival manual left behind by chance. The number makes sense only because we are here to ask about it. This is the anthropic principle, the unsettling idea that the universe must appear fine-tuned to us, because only in such a tuned universe could observers like us emerge. But that answer doesn't satisfy. It explains away wonder with logic and trades depth for circularity. It tells us, you see this number because otherwise you wouldn't exist, without letting us touch the machinery behind the curtain. And so, the question lingers, not just as a scientific puzzle, but as a philosophical wound. Why this mass? Why this particle? Why this universe? If reality is a book, then the electron's mass is a sentence that was written by someone we've never met, in a language we only partially understand. We highlight the phrase, we quote it in our papers, we use it to build models, but we don't know what it truly means. And maybe we never will. Maybe there are answers out there, waiting in some deeper layer of physics we haven't yet uncovered. Or maybe the answer isn't a number at all. Maybe it's a realization that the limits of science aren't walls but mirrors, showing us not just what we don't know, but who we are when faced with the unknown. The electron, in all its tiny mystery, becomes a symbol for everything unfinished in our quest to understand. A constant whisper reminding us that the universe still keeps secrets. And among them, tucked in the fabric of every atom, is a mass we can't explain, but owe everything to: the quantum vacuum. It's full of energy, but unobservable. Imagine standing in a cathedral of absolute silence, not a whisper, not a breath, not even the ghost of sound, and being told that beneath your feet, behind the stone walls, inside, the marble pillars, and woven into the sacred emptiness itself, there's a roaring storm of energy so dense, so wild, so ceaselessly alive that it could, with the slightest twitch, give birth to stars, galaxies, or perhaps an entire universe. That's the paradox we're stepping into now. The mystery of the quantum vacuum. The term itself is misleading, almost a cruel joke. Vacuum suggests emptiness, a place where nothing exists, a blank canvas of reality. But in the quantum world, emptiness is an illusion. What we think of as a void is actually a seething, restless ocean of energy, pulsating with virtual particles, flaring into existence and vanishing again before you can even conceive of their presence. You're about to dive into one of the strangest truths ever uncovered by science, that the fabric of nothingness is in fact not nothing at all. And this idea isn't hypothetical, it's measurable, powerful, and possibly more foundational than matter itself. The journey into the quantum vacuum is not just a scientific investigation, it's a philosophical assault on our understanding of reality. From the earliest days of classical physics, we built our intuition around the idea that empty space was truly empty. Aristotle declared that nature abhors a vacuum. Newton imagined space as a passive stage, a neutral backdrop for forces and motion to play out upon. Even in Einstein's general relativity, space-time is malleable, but still fundamentally a container. But quantum mechanics tears this illusion to shreds. It tells us that even in perfect vacuum, at absolute zero temperature, with all particles removed, no light, no heat, no sound, there is still activity, still fluctuation, still energy. The vacuum is not a backdrop, it's a protagonist. It creates, it influences, it interacts. And we've seen the evidence, the Casimir effect, where two metal plates placed close together in a vacuum attract each other, not because of gravity or electromagnetism, but because the quantum vacuum pushes them together. The Lamb shift, a tiny energy difference in the hydrogen atom, again caused by the vacuum. These aren't theoretical curiosities, they're observable facts. They are proof that even in nothingness, something is happening. But how can something exist where nothing is supposed to be? This is where things get strange. In quantum field theory, every type of particle is associated with a field that extends throughout space. Even when there are no particles present, these fields are still there, and they're never completely at rest. They fluctuate. These fluctuations are responsible for what we call zero-point energy, the lowest possible energy a quantum system can have. But lowest doesn't mean zero, it means minimum. That's crucial. There is always energy present, even in the quietest, coldest, most deserted corner of the universe. And these fluctuations cause virtual particles, temporary blips of existence that appear and disappear too quickly to be directly detected, yet still influence reality. Imagine waves crashing on a beach that has no ocean. That's what this is like. You don't see the water, but the foam still erupts into being, leaves its mark and dissolves back into nothing. It's not just poetic, it's literal. These phantom fluctuations create a restless sea beneath the surface of our cosmos. Now here's where it becomes even more mind-bending. The quantum vacuum might actually determine everything. Some physicists believe that all forces, particles, and interactions, the very structure of matter and energy, arise from how different quantum fields interact with the vacuum. It's not just a passive medium, it might be the architect of the universe. In inflationary cosmology, the early universe is thought to have expanded faster than light due to the energy of the vacuum. When this vacuum energy decayed, it released a flood of particles and radiation, filling the universe with matter. In this view, everything we see today, galaxies, stars, atoms, is the cooled-down aftermath of a phase transition in the vacuum. The vacuum changed its state, like water freezing into ice, and that change was creation. This is not an abstract, a metaphor. It's one of the leading explanations for why there is something rather than nothing. And yet, despite its foundational role, we can't see the quantum vacuum. We can't measure its energy directly. And this creates a paradox, one of the greatest in modern physics. Quantum field theory predicts that the vacuum should have an enormous amount of energy, perhaps 120 times greater than what we observe in our universe. That's a 1 followed by 120 zeros. But when we look at the universe's expansion, we find that the actual vacuum energy, the so-called cosmological constant, is tiny. This discrepancy is so vast that it's been called the worst theoretical prediction in the history of physics. Something is terribly wrong. Either our understanding of quantum fields is incomplete, or something is cancelling out the vacuum energy in ways we don't yet grasp. Some theories suggest hidden symmetries. Others invoke the multiverse, proposing that we live in one of many universes, and ours just happens to have a small vacuum energy by chance. None of these answers are satisfying, and that should terrify us in the best way possible. Because if the vacuum is wrong, everything might be wrong. Or more accurately, everything might be more right than we can currently imagine. The vacuum isn't just a stage. It might be the scriptwriter, the director, the producer, and the stage itself. The vacuum might be the medium from which time and space emerge, not merely exist within. In some theories of quantum gravity, space-time is not fundamental. It's emergent, from entangled quantum information, from the relationships between particles, from the vacuum. That means that what we think of as reality is a byproduct of something deeper, stranger, and invisible. The vacuum, the so-called emptiness, is the hidden canvas upon which the illusion of form is painted. Think of it like a theatre performance. You watch the actors, the lights, the story, but what you don't see, the stage, the ropes, the crew in black moving silently behind the curtain, that's what makes the illusion possible. The quantum vacuum is the invisible crew of the cosmos, pulling strings you don't know exist, shaping outcomes without applause or recognition. It doesn't ask to be noticed. It doesn't shine. It simply is. And in being, it holds more power than anything you've ever encountered. So next time you look at an empty room, remember, it's not empty. The silence isn't silent. The stillness isn't still. The vacuum of space isn't void. Beneath every breath you take, behind every photon of light, in every space between every atom, there is a raging ocean of invisible energy, bubbling, with possibility, echoing the first tremble of creation itself. It's not nothing, it's everything. Why neutrinos oscillate between types. You are walking through a crowd, thousands of strangers brushing past you, but one catches your eye, only for a second. You blink, and suddenly, they're gone. But then, 10 steps later, there they are again. Or maybe someone just like them. Same height, same jacket, same strange presence. But they're not quite the same. It's as if the person you thought you saw is constantly shifting just out of certainty. You begin to question your memory, your senses, your perception of continuity. This unsettling feeling of something that's there, but never quite what, it seems, is exactly the kind of illusion that neutrinos, the shyest particles in the universe, perform constantly. Every second, trillions of them pass through your body, through the Earth itself, as if matter doesn't even exist. They are so indifferent to the physical world that they rarely leave a trace. But behind that indifference lies one of the strangest, most elegant behaviors in all of physics: neutrino oscillation. The ability of a neutrino to transform from one type into another as it moves through space. like a ghost shifting masks mid-performance without ever pausing the dance. It's not that we don't know neutrinos exist. We do. We've detected them. But we didn't expect them to morph. It would be like discovering that someone you've known for years can casually change their DNA, their voice, their entire identity every few minutes and still claim to be the same person. This revelation shocked the world of particle physics, because for decades we assumed particles were stable categories, defined by their type. A neutrino was either an electron, neutrino, a muon neutrino, or a tau neutrino. End of story. But neutrino oscillation broke that story open. Suddenly, particles were no longer labels, they were probabilities. Being a type became a fluid concept. Neutrinos blur the boundaries between identity and transformation. But why does this matter? Because to understand neutrino oscillation is to confront one of the most mysterious aspects of the quantum world, that identity is not fixed, but contingent on time, space, and the act of measurement. It's not just a particle's name that changes, it's the very basis of what it means to be something. And what's behind this transformation is not magic, but a strange quantum superposition. Neutrinos are created in a mix of mass states that don't align perfectly with their flavor states. Imagine trying to walk east while wearing shoes that only point north. Your body moves in one direction, but your feet pull another. The result is a strange zigzag, a constant drift. Similarly, as neutrinos travel, the components of their quantum identity interfere with each other, and over time, this interference causes the dominant identity to shift. What begins as an electron neutrino might become a muon neutrino by the time it reaches a detector. It's like a song that starts in one key and, by the time you finish listening, has modulated into an entirely different mood. And we can't even predict the transformation with certainty. We can only speak in probabilities. This uncertainty has massive implications. It tells us that neutrinos have mass, something we didn't know for sure until the 1990s. For decades, the standard model of particle physics treated them as massless. Oscillation shattered that assumption. And since the masses of neutrinos are still unknown, still imprecisely measured, they remain one of the biggest gaps in our understanding of matter. But there's more. Neutrino oscillation might be the key to solving one of the deepest mysteries in cosmology: why the universe exists at all. According to the laws of physics, matter and antimatter should have been created in equal amounts during the Big Bang, annihilating each other in a perfect cancellation. And yet, here we are, an entire universe made of matter. One possible explanation involves a phenomenon called leptogenesis, which hinges on neutrino behavior. If neutrinos behave differently from antineutrinos, perhaps violating a symmetry called CP, charge parity, it could explain the imbalance that led to a matter-dominated universe. In other words, the identity crisis of a ghostly particle may be the reason reality didn't cancel itself out. But the deeper you go into the quantum mechanics of oscillation, the more uncanny it becomes. Neutrinos don't switch identities. At a particular point, they exist in a liminal space, both themselves and not, until measured. It's a bit like Schrödinger's cat, except instead of being dead or alive, the neutrino is muon or electron or tau, or some ghostly mix in between. This dance of identities unfolds as a function of time, distance, and mass-squared differences, and yet we can't observe it directly. We only ever see the beginning or end of the process. The middle, the transformation itself, is a secret the universe refuses to show. That's the strange poetic cruelty of it. Neutrinos tell us that identity is a process, not a fixed trait. That change is not something that happens to particles, but something they embody. They are quantum shapeshifters, born in flux, thriving in ambiguity. Their transformations whisper of a universe where nothing is truly constant, where even the most fundamental elements of matter are stories in motion. When we talk about neutrino oscillation, we are not just discussing subatomic mechanics. We are confronting the nature of identity itself. And in a way, aren't we all like neutrinos, moving through life, environments, relationships, identities? shifting from one role to another, never fully defined by a single moment or measurement. Who you were a year ago isn't exactly who you are now, and who you'll be tomorrow is an oscillation away. Neutrinos remind us that identity is not a fixed point, but a waveform. We are not nouns. We are verbs, not things, but processes. And if the smallest, quietest particles in the universe can embody this truth, maybe we can, too. Maybe the lesson of the neutrino is that transformation isn't a failure of consistency, but the most fundamental law of being, the mass gap problem. No mathematical proof exists for mass in quantum fields. Imagine standing at the edge of an ocean at night, watching waves crash against the shore under a sky scattered with stars. Each wave is different in shape and size, but all obey the same unseen rhythm of the moon's gravity. Now imagine that beneath this ocean lies a deeper sea, one that you cannot see, cannot touch, cannot even measure directly, but which generates the surface waves above. This is what the quantum world is like. Beneath the particles we think we understand, electrons, quarks, photons, there exists a deeper field of vibrating potential. And the most mysterious of all is this. Some of those vibrations manifest as massless ripples, while others emerge with weight, resistance, and consequence. Why? The question sounds simple, almost naive. Why do some particles have mass while others do not? And why, even though our equations predict massless behavior, do we observe massive particles instead? This enigma is what physicists call the mass gap problem. In the abstract dance of quantum fields, mass should be a straightforward feature. But in quantum chromodynamics, QCD, the theory that governs the strong nuclear force, there's a jarring dissonance. The math tells us that gluons, particles responsible for binding quarks into protons and neutrons, should be massless, and yet they never appear alone. They are always confined, hidden, their effects observable only indirectly. Even more troubling is that we know massive particles must exist. We detect them, we measure their mass, we build entire models around them, and yet we have no mathematical proof that explains why. That gap between prediction and observation is what haunts the foundations of physics, like a ghost in the machine. It's the invisible crack in the cathedral of our understanding, the flaw that makes the whole structure tremble. To appreciate the magnitude of this riddle, we need to understand how we typically deal with particles and forces. Quantum field theory treats particles not as little billiard balls, but as excitations in underlying fields, much like a ripple on the surface of a pond. Electrons are excitations in the electron field, photons in the electromagnetic field, and so on. When energy condenses in just the right way, it creates a particle. And within this framework, the Higgs field provides an explanation for how particles acquire mass, but only some particles. It doesn't explain why composite particles like protons and neutrons have the mass that they do, nor why certain fields remain massless. The strong force mediated by gluons is a perfect example. Gluons are predicted to be massless, and yet the particles they hold together, hadrons, have mass. More curiously, gluons can't exist in isolation. They are always confined within larger particles due to a phenomenon called color confinement. The equations governing this process are deeply nonlinear and chaotic, making exact solutions impossible with current methods. That's where the mass gap problem comes in. It's the difference between the zero-mass gluons predicted by the theory and the non-zero mass of the hadrons we actually observe. It's not a philosophical gap. It's a quantitative, measurable hole in our best understanding of the universe. And worst of all, no one has been able to prove mathematically that this gap must exist. It's one of the Clay Mathematics Institute's 7 Millennium Prize problems, which means solving it comes with a $1 million prize, and more importantly, it would cement our understanding of how mass emerges from the quantum world. But the problem is deeper than money or prestige. It speaks to something existential, the reliability of our physical laws. If we cannot mathematically prove that mass emerges from a theory we trust to build the atomic nucleus, then what does that say about the limits of our knowledge? Imagine building a house on solid rock, only to realize years later that the foundation you trusted was in fact suspended over a chasm. The house may still stand, but now you live with the anxiety of not knowing why. That's the emotional reality for many theoretical physicists when they think about the mass gap. It's a constant reminder that some truths are felt before they are understood, observed before they are explained. The tools of quantum field theory, path integrals, gauge symmetries, renormalization, are powerful, but they remain incomplete without this missing piece. It's like writing a symphony and leaving out the final chord, or constructing a cathedral without placing the keystone. We can simulate parts of the theory using lattice QCD, breaking space-time into discrete chunks and computing the interactions. But this still isn't the same as a formal mathematical proof. It's as if we're peering at the truth through a frosted window. We see its shape, we sense its weight, but its edges are always blurred. And yet, what makes the mass gap problem so haunting is not just the absence of proof, but the certainty of the effect. It's not that we think mass emerges from quantum fields. We know it does. We measure it every day in particle accelerators. We build technologies, medical devices, and even theories of cosmology around it. We know that protons and neutrons, the building blocks of all atoms, get most of their mass not from the quarks inside them, but from the energy that holds those quarks together. That energy, described by the equations of QCD, is what becomes mass through Einstein's famous equation E mc2. So the mass isn't a fundamental property of the quarks themselves, but a manifestation of the binding energy that comes from the strong force. And here's the kicker. The theory that gives us this binding energy predicts that gluons are massless and that their self-interaction should confine them, creating massive bound states, but we can't prove it. We're stuck in a strange limbo, where theory and observation dance around each other like partners in a waltz, perfectly in sync, yet never touching. Every attempt to close that gap mathematically has run into walls of complexity, infinities, and unsolved assumptions. Some approaches involve Yang-Mills theory, a subset of gauge theories that describe these interactions, but proving that Yang-Mills theories possess a mass gap, that there exists a non-zero lowest energy state distinct from the vacuum, is the challenge that still eludes us. So where does that leave us? In a world that's simultaneously precise and uncertain. A world where we can split atoms, chart galaxies, and simulate the birth of the universe, but still can't prove why a neutron has mass. The mass gap problem reminds us that our deepest tools still fall short. That even in the age of quantum computers and gravitational wave detectors, some of nature's secrets remain sealed. But perhaps there's something poetic in that. Maybe the universe isn't just a puzzle to be solved, but a story to be lived. Maybe the gap between what we see and what we know is where wonder lives. The mass gap is more than just a mathematical curiosity. It's a philosophical invitation. A reminder that science, at its heart, is not about certainty, but about the pursuit of understanding. About standing at the edge of the ocean and listening to waves you can't see, feeling rhythms you don't yet comprehend, and trusting that one day the tide will reveal what lies beneath. The muon anomaly. A particle behaves differently than expected. What if I told you that the universe, for all its precision, for all its predictable rhythms and mathematical elegance, might be harboring a crack in its foundation? One so small that it hides within the spin of a single subatomic particle, yet so profound that it could unravel everything we thought we understood about nature itself. Picture a violinist playing in a symphony where every note has always aligned, every movement has always been orchestrated, and every crescendo predictable to the millisecond. Now imagine, in the middle of this grand performance, one note subtly bends out of tune, not off key enough to disrupt the entire concert, but just enough to be noticed by the most sensitive ear. That single anomaly, if true, wouldn't mean the violinist made a mistake. It would mean the music itself might have new rules. That's the muon anomaly. The muon, a heavier cousin of the electron, should behave predictably, according to the well-polished equations of the Standard Model, the prevailing theory that has governed particle physics for half a century, but it didn't. In an ultra-precise experiment conducted at Fermilab, muons behave just a little differently. Their magnetic wobble, known as the anomalous magnetic moment, was slightly off, measured more precisely than ever before, yet deviating from theoretical predictions by a sliver so small it could have been dismissed. But it wasn't, because in physics, a sliver is everything. The most revolutionary ideas have grown from the smallest inconsistencies: Newton's apple, Einstein's elevator, and now perhaps the muon's wobble. In that fraction of difference, just parts per billion, lurks a possibility that the Standard Model is incomplete, and if it is, then so is our entire map of reality. That wobble isn't just a quirk of nature, it's a whisper from the universe that there may be more. More particles, more forces, more dimensions, more truth. But what exactly is this anomaly, and why has it shaken the scientific community to its core? To understand the depth of this mystery, you have to understand the confidence we once had. The Standard Model has predicted the behavior of particles with extraordinary accuracy. It's the framework that has helped us build everything from medical imaging to the Large Hadron Collider. It categorizes particles into quarks and leptons, mediators like photons and gluons, and even accounts for the Higgs boson, which was predicted long before it was observed in 2012. For decades, it seemed unshakable. But like any map, its perfection was only as good as its resolution. And when we zoomed in closer, into the intricate spin of a muon, something didn't match. The muon has a property called spin, much like the Earth rotates on its axis, and this spin causes it to behave like a tiny magnet. When placed in a magnetic field, it should wobble, precess, at a very specific rate, which can be predicted with pinpoint precision using quantum electrodynamics, quantum chromodynamics, and electroweak theory. But the observed precession rate was just a little higher than predicted. It was as if the muon was being nudged by something invisible, something not accounted for in our equations. Could it be a new particle? A hidden force? The shadow of a fifth fundamental interaction? This wasn't the first time such whispers had been heard. Similar results were observed at Brookhaven National Laboratory in 2001, but the statistical significance wasn't enough to declare a discovery. Fermilab, with upgraded equipment and more muons, sought to confirm the anomaly, and they did. Not only was the deviation confirmed, it now stood on the threshold of discovery. In particle physics, a 5 sigma deviation, meaning a 1 in 3.5 million chance of it being a fluke, is needed to declare new physics. The muon anomaly is now hovering around 4 sigma, meaning the evidence is mounting. But beyond the statistics lies the philosophical rupture. What if the model that has explained every interaction we've ever observed is missing something fundamental? And what if that missing piece isn't just a technical footnote, but an entire new chapter in the book of existence? One of the theories that gained traction in the wake of this anomaly is supersymmetry, a bold idea suggesting that every known particle has a heavier twin, a superpartner, yet to be discovered. If supersymmetric particles exist, they could explain not only the muon's behavior, but also dark matter, which makes up 85% of the universe and yet has never been directly observed. In this light, the muon isn't just misbehaving, it's trying to show us what's hiding in the shadows. Another candidate is the idea of a dark photon, an unknown force carrier that interacts with dark matter and might slightly influence the muon's spin. Or perhaps we're on the verge of discovering a fifth fundamental force, joining gravity, electromagnetism, and the strong and weak nuclear forces, a force that subtly alters the behavior of particles under specific conditions. Whatever the answer is, the anomaly suggests the possibility of entirely new realms of physics, like discovering a hidden room behind a wall you thought was solid. And here's where things become beautifully poetic. The anomaly isn't grand or dramatic. It's barely perceptible. It lives in the margins, in the decimals. And yet, it might reveal more about the universe than the most spectacular supernova or black hole. It's a reminder that nature doesn't always scream her secrets. Sometimes, she whispers. But perhaps the most haunting part of this story isn't just what we're discovering. It's what it reveals about how we discover. Because the muon anomaly shows us that science, for all its rigor, is still a living, breathing, evolving endeavor. It's not a set of final answers carved in stone. It's a dialogue between us and the cosmos. And sometimes it's the tiniest stutter in that dialogue that forces us to rewrite everything. When the muon wobbled unexpectedly, it did more than shift the needle of an instrument. It shook our sense of certainty. And maybe that's why it resonates so deeply. Because in our own lives, we too encounter anomalies. Moments where what's happening doesn't align with what we expected. A sudden change in someone we love. A feeling we can't explain. A dream that refuses to fade. We dismiss these things, just like physicists once dismissed the muon's deviation. But perhaps, like in physics, our most profound revelations lie hidden in those discrepancies. Maybe the key to growth, to truth, to understanding of the world, of ourselves, is in daring to ask why something doesn't fit. So what happens next? That depends on what we're willing to pursue. More data is being collected. More refined calculations are being made. And yet the path forward isn't just about labs and equations, it's about perspective. Do we cling to our current models, insisting that the muon must be wrong? Or do we listen closely, courageously, to what the universe might be trying to tell us? And isn't that the essence of science? Not the pursuit of certainty, but the willingness to question, to revise, to grow. The muon anomaly doesn't prove new physics yet, but it dares us to imagine it. It opens a door, a crack in the wall through which light might enter. And maybe, in that light, we'll see not only the next layer of the universe, but a deeper reflection of ourselves. Because ultimately, the story of the muon is the story of attention, of what happens when we look closer, of the miracles we find when we don't dismiss the details. That particle, spinning silently in a magnetic field, is doing something no one expected. And that makes it, perhaps, one of the most honest teachers in the cosmos. Not because it offers answers, but because it reminds us to stay curious, to follow the anomalies, to believe that sometimes, when something doesn't make sense, it's not a mistake. It's a message. So listen closely. The universe is still speaking, and the muon, it's whispering something extraordinary. Are there undiscovered forces beyond the four we know? You've been told that the universe is governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Four invisible puppeteers behind. Every falling apple, every lightning bolt, every fusion reaction inside the sun. You've been taught that these are the pillars of nature, the invisible architecture beneath every galaxy, every atom, every breath you take. But what if that's not the whole story? What if the universe is holding something back? Imagine living your entire life in a house with 4 rooms, thinking you've explored every corner, only to discover, one quiet morning, a hidden door behind the wallpaper. You open it, and what you find doesn't just add a room, it changes your understanding of the entire house. This is the suspicion growing quietly in the minds of physicists around the world, that there may be more than just 4 forces shaping our reality, that a 5th or even 6th force might be hiding in the shadows, operating silently, eluding detection, and subtly rewriting the rules we thought were absolute. This isn't science fiction. It's a real, measurable possibility. And it may be the key to unlocking some of the greatest mysteries we've ever faced. The puzzle of dark matter, the acceleration of the universe's expansion, the strange behavior of certain particles, and even the very question of why anything exists at all. The story begins, as it often does in physics, with something that didn't quite add up. In the quiet halls of labs around the globe, experiments have been whispering inconsistencies, subtle deviations in measurements, unexplained signals, behaviors that don't align with our best equations. The standard model of particle physics, though immensely successful, leaves too many questions unanswered. Why does gravity feel so weak compared to the other forces? Why is 95% of the universe, dark matter and dark energy, still a mystery? Why do some particles, like muons, behave in ways that theory can't explain? These are not minor gaps. They are chasms, and every now and then, a glimmer from the unknown slips through. In 2016, researchers in Hungary observed an anomaly in the decay of an excited state of beryllium-8, an unexpected bump in the distribution of emitted particles that didn't fit known physics. It suggested the presence of a new particle, a potential messenger of a fifth force, something not electromagnetic, not nuclear, not gravitational. It was dubbed the X-17 particle, a name that reflected both its mass and its mystery. Though the results have yet to be confirmed elsewhere, the anomaly opened the door to a question long whispered but rarely spoken aloud. Are we missing something fundamental? Because if there is a fifth force, it would be unlike anything we've encountered before. It might only interact with dark matter, rendering it invisible to our current detectors, or it could operate over microscopic distances, hiding beneath the noise of our instruments. It could be a force of symmetry restoration, an echo from the universe's infancy, or something woven through the extra dimensions predicted by string theory, invisible to us, yet vital to everything. And the implications are staggering. Our understanding of reality is scaffolded on the assumption that we know the complete set of interactions that govern it. Introduce a new force, and everything shifts. The cosmic web connecting galaxies, the stability of atoms, the evolution of the early universe, all would need to be re-examined. We are, in a sense, attempting to complete a jigsaw puzzle with several pieces missing, and every new force discovered could be one of those missing fragments, turning confusion into clarity, silence into meaning. But these fragments are elusive. They don't announce themselves with fireworks. They whisper. They hide in the decimals, in the unexplained corners of particle collisions, in the drift of galaxies that don't behave as they should, in the shadows cast by equations that don't quite close. But the mystery of hidden forces doesn't only reside in accelerators or observatories. It resides in a deeper, more philosophical question. What does it mean to know the universe? We think of science as a steady climb toward truth, a process of refining our understanding until only the purest principles remain. But what if that climb occasionally takes us to plateaus, where everything seems finished, solid, final, until suddenly a crack appears beneath our feet, revealing another climb, steeper and stranger than before? History has shown us this over and over. Newton believed he had found the final laws of motion until Einstein came along. Einstein believed in a static universe until Hubble's telescope revealed its expansion. Time and again, our models have felt complete until they weren't. And the discovery of a new force wouldn't just be another revision. It would be a revolution. It would be the kind of shift that turns certainty into curiosity, that rewrites textbooks and reorients philosophies. It would challenge not just our physics, but our assumptions about control, predictability, even meaning, because forces aren't just theoretical constructs. They are the invisible hands behind everything we do. They hold our bodies together, power our thoughts, light our skies. To discover a new one would be to discover a new part of ourselves, and that brings us to something more intimate, something the equations can't capture, our deep, aching desire to feel that we understand the world, to feel that the chaos around us is governed by something intelligible, something we can name, model, trust. And when the rules we rely on begin to fray, when particles behave strangely, when galaxies drift too fast, when decay patterns defy logic, it unnerves us. But it also invites us, because at the edge of our understanding lies not just confusion, but beauty. The beauty of a universe that refuses to be simple, that resists being fully known. that always holds something back. And in that resistance, in that refusal to be pinned down, is where wonder lives. Not in the answers, but in the questions. Not in the forces we've defined, but in the ones still unnamed. So are there undiscovered forces beyond the four we know? We don't know, not yet. But the hints are there. In the magnetic spin of muons, in the unexplained decay of atomic nuclei, in the gravitational behavior of galaxies we can't see, in the fabric of space-time itself, which may ripple not just with waves of gravity, but with the tremors of something else, something still unseen, still unnamed, still waiting. And maybe that's the most honest place science can take us, not to finality, but to the threshold of wonder, to the realization that the more we discover, the more we realize how much remains hidden. And maybe, just maybe, the forces we haven't found yet aren't just physical. Maybe they're emotional, existential, metaphysical. Maybe they're reminders that we are not just observers of the universe, but participants in its unfolding, guided not only by logic, but by longing. Because, in the end, the question of undiscovered forces isn't just about particles and fields. It's about our willingness to remain open to being wrong, open to being surprised, open to the possibility that the universe is still far stranger than we can imagine. It's about listening, not just to data, but to doubt. And it's about following those faint, flickering signals, those quiet deviations and anomalies, not with fear, but with awe. Because the universe isn't finished. It's unfolding. And somewhere, in that unfolding, a new force may be waiting. Not just to change our equations, but to remind us why we began asking questions in the first place. The axis of evil, a strange alignment in the cosmic microwave background. Sometimes the strangest mysteries don't lie in the vast unknown, but in the patterns we thought were random. Imagine standing before an ancient tapestry, woven not by human hands, but by the cosmos itself. It stretches endlessly in every direction, the background of everything that exists. And you've always believed that this tapestry is chaotic, evenly stitched, unpatterned, free from bias, because that's what science predicted. But then, one day, someone notices that certain threads seem to be lined up. Not just once, not by coincidence, but again and again, forming an eerie, persistent alignment that defies everything we expected. That's what scientists discovered when they stared deep into the afterglow of the Big Bang, the faint microwave whisper that fills the entire universe, known as the cosmic microwave background, or CMB. This signal is supposed to be our most unbiased, most pristine window into the early universe. It should be smooth, isotropic, directionless, but it's not. When we looked closely, we saw something we weren't supposed to see. A strange alignment of temperature fluctuations stretching across the sky, pointing in one particular direction. A cosmic asymmetry dubbed, half-jokingly, the axis of evil. But this is not science fiction. This is real data, and the more we've tried to dismiss it as coincidence, noise, or error, the more persistently it remains. What does it mean when the most ancient light in the universe appears to have a preferred direction? What does it mean when the map of the cosmos looks rigged? To understand how unsettling this is, you need to know what the CMB really is. Roughly 13.8 billion years ago, our universe was born in an unimaginably hot and dense state, what we call the Big Bang. For the first 380,000 years, the universe was a foggy, opaque soup of particles, too hot for light to travel freely. But then, as it cooled, photons broke free and began their endless journey across space. Those ancient photons are still traveling, still arriving, and we can detect them today with radio telescopes. They form a near uniform glow in every direction of the sky, the CMB. But it's not perfectly uniform. There are tiny fluctuations in temperature, variations of just 1 part in 100,000, that tell us about the density variations in the early universe. These fluctuations gave rise to galaxies, stars, planets, and ultimately us. According to the cosmological principle, These fluctuations should be statistically random and evenly distributed. No preferred direction, no cosmic up or down. But when NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and later the ESA's Planck satellite mapped the CMB in stunning detail, they both found something chilling. The largest scale fluctuations, the quadrupole and octupole moments, weren't random. They were aligned. Aligned not just with each other, but with the ecliptic, the plane of Earth's orbit around the Sun. This isn't supposed to happen. The universe shouldn't care about the orientation of our solar system. The CMB should be indifferent to us. And yet, the data shows otherwise. This alignment, which spans vast swaths of the sky, suggests the universe might have a preferred axis, an idea that runs directly counter to the core assumptions of modern cosmology. If confirmed, it would mean that the universe is not isotropic, that it has a direction, a structure, a hidden order that we've never accounted for. And this possibility sends shockwaves through everything we thought we understood. Because the entire framework of cosmology is built on the idea that the universe is, on large scales, the same in every direction, that no location is special, that no angle is preferred. But the axis of evil suggests otherwise. It suggests a hidden hand, a cosmic pattern, baked into the very fabric of space-time itself. And the implications are staggering. If the early universe was lopsided, if there was a tilt or twist in the primordial fabric, it could mean our models are fundamentally flawed. It could affect our measurements of the Hubble constant, the curvature of space, the nature of dark energy, and even the origin of cosmic inflation. It might imply that our universe isn't just expanding, it's rotating, or that it emerged from a collision with another universe, or that the Big Bang wasn't entirely random, but seeded with directionality from the very beginning. Of course, scientists are cautious. Many have proposed mundane explanations. Maybe it's an artifact of the way we process the data. Maybe foreground contamination from our galaxy is distorting the signal. Maybe it's just a statistical fluke, an unlikely but not impossible coincidence. But here's the problem. Multiple independent satellites with different instruments and different analysis methods have seen the same thing. The alignment remains, and the probability of it occurring by chance, less than 0.1%. It's like flipping a coin 100 times and getting heads 90 of them. You could argue it's luck, but eventually you begin to suspect the coin is weighted. And if the coin is weighted, if the universe truly has an axis, it raises a much deeper question. What else have we misunderstood? Because in a way, the axis of evil is not just a data point, it's a mirror, a reminder of how deeply we want the universe to be fair, balanced, symmetrical. Symmetry is reassuring. It suggests that the laws of nature are impersonal, universal, democratic. But maybe nature isn't that polite. Maybe the cosmos has a scar, a memory, a twist in its bones that breaks the illusion of symmetry. Maybe the story we've been telling, that of a perfect, directionless expansion, is a simplified myth, a mathematical lullaby we sing to quiet our fear of the unknown. And if that's true, then the axis of evil isn't just a technical anomaly. It's a philosophical rupture. It forces us to confront the idea that the universe might be structured in ways we weren't prepared to imagine, that the cosmos might carry secrets not just in its depths, but in its shape, in its angle, in its alignment. And isn't that, in some strange way, a reflection of our own experience? We like to think of ourselves as rational, symmetrical, balanced, but our lives too have axes, traumas, memories, alignments we can't explain. We carry invisible structures that shape how we think, how we love, how we fear. The universe may be doing the same, and perhaps, just as we must confront our own hidden patterns to grow, science too must confront the uncomfortable alignments in its most sacred data. So what happens next? For now, we keep looking. Future missions, like Lightbird and CMB-S4, may shed more light or more shadow. We refine our models, we question our assumptions, We accept that even our cleanest maps may be messier than we hoped, but more importantly, we remain open to the idea that the cosmos may be more than equations and probabilities, that it may have quirks, asymmetries, even preferences, that it may, in some deep sense, be alive, not in the biological way, but in the way that all systems with memory and motion possess a kind of narrative. And perhaps the axis of evil is one chapter in that narrative, a strange, persistent thread in the tapestry that refuses to be ignored, a reminder that even in the oldest light of the universe, mystery endures. And maybe that's the real beauty here. Not that we've found the answer, but that we've found a question bold enough to reshape our thinking, a question that whispers from across the stars. What if the universe isn't neutral? What if it remembers? What if it points? And what if it's pointing at us? Not with meaning, not with intent, but with a quiet dare to look deeper, to think wider, to imagine more. Because in the end, the axis of evil may not be evil at all. It may simply be the universe telling us, you don't know me yet, not fully, not deeply, but keep asking, keep staring into the static, keep mapping the silence. Because somewhere, in those subtle alignments and ancient echoes, the next great truth is waiting, patient, strange, and utterly real. Why fundamental forces differ so much in strength. If you've ever tried to hold a magnet close to a paperclip, you've seen it. How, with a gentle pull, the magnet lifts the metal without touching it, as if space itself bends in quiet obedience. Now, consider this. With that tiny gesture, the magnet just overpowered the entire gravitational pull of the Earth. A fridge magnet, casually defeating a planet. It sounds ridiculous, but it's true. And in that quiet moment lies one of the greatest, unsolved mysteries in physics. Why do the fundamental forces of nature differ so drastically in strength? Why is gravity, which holds planets in orbit and warps space-time itself, billions of times weaker than electromagnetism, which lights our cities and drives the chemistry of life? Why does the strong nuclear force keep protons from flying apart, inside the atom's heart, with almost violent intensity, while the weak force shuffles particles around like an indecisive host at a quantum dinner party? This disparity isn't just a curiosity. It's a puzzle buried deep within the foundations of the universe. A puzzle that quietly shapes everything we know, everything we are, and everything that might be. To understand how strange this imbalance is, imagine a room with 4 voices, each one representing a fundamental force: gravity, electromagnetism, the strong force, and the weak force. Now imagine that one of those voices, gravity, is whispering almost inaudibly in the corner, while another, the strong force, is shouting with thunderous volume. The other two, electromagnetism and the weak force, speak somewhere in between, each with their own volume and flavor. The odd part is, they're all supposed to be reading from the same script. They're all governed by the same principles of quantum field theory, all thought to be different expressions of a deeper, unified language. And yet, they don't behave as equals. They vary not by a factor of 2 or 10, but by quadrillions. These aren't casual mismatches. These are cosmic imbalances on a scale that defies intuition. So physicists ask, again and again, why? Why does nature choose to speak so loudly with some forces and barely whisper with others? In the standard model of particle physics, each force arises from a different field and is mediated by a different set of particles. Photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force, and, theoretically, gravitons for gravity, though we've never observed them. These force carriers are like messengers that deliver interactions from one particle to another. But here's where it gets strange. The strength of these interactions, what we call the coupling constants, is wildly different. The strong force is about 1039 times more powerful than gravity. 10,000 billion times more. That's not a typo. That's the scale we're talking about. And yet, without this hierarchy, you wouldn't exist. If gravity were even slightly stronger, stars would collapse too quickly. If the strong force were weaker, atomic nuclei couldn't form. If the electromagnetic force were off, chemistry would fail. Life, as we know it, relies on this delicate, seemingly arbitrary disparity. So again, we ask, is it a coincidence, a fluke of cosmic dice? Or is there a deeper reason we haven't yet seen? One possibility is that the forces weren't always so different. That in the searing heat of the early universe, just moments after the Big Bang, all forces were united, equal, indistinct, harmonized. This idea is at the heart of grand unified theories, or GUTS, which propose that at high enough energies, the strong, weak, and electromagnetic forces merge into one single force, only to break apart as the universe cools. Like ice forming out of water, symmetry breaks and separate forces emerge. If this is true, then the wild differences in strength we see today are the frozen echoes of a deeper unity long past. But gravity resists even this theory. It doesn't fit easily into GUTS. It remains stubbornly outside the club. And that's led some physicists to speculate that gravity isn't a force like the others. It's something else entirely. Perhaps an emergent phenomenon, like temperature, which arises from the collective behavior of particles but doesn't exist at the microscopic level. Maybe gravity isn't fundamental, but a shadow, an echo of information geometry, entropic interactions, or holographic principles projected from deeper dimensions. Then there's the hierarchy problem, a thorn in the side of theoretical physics for decades. It asks, why is the Higgs boson's mass so small compared to the Planck scale, where gravity becomes strong? Quantum corrections should make the Higgs mass balloon unless it's finely tuned. Absurdly so. It's like balancing a pencil on its tip during an earthquake and having it stay perfectly upright. Supersymmetry, extra dimensions, technicolor, all have been proposed to solve this, but none have been proven. The forces don't just differ, they differ in a way that seems unnaturally precise, almost engineered. And this idea, while controversial, has led some to ask whether the universe is fine-tuned, not necessarily for life, but for coherence. That in a multiverse of countless possible realities, we happen to exist in one where the balance of force, strengths permits complexity. It's not a comforting idea. It doesn't offer a reason, but it offers an explanation of sorts. And yet, despite these theories, the question remains viscerally unsolved. Why should one force sculpt the nuclei of atoms while another gently guides moons around planets? Why should a single photon live forever while a W boson decays in less than a trillionth of a second? Why such imbalance? Why such hierarchy? Why such exquisite asymmetry? These aren't just equations, they're existential questions, because the answer shapes everything. It shapes whether stars burn or collapse, whether galaxies form or evaporate, whether life arises or vanishes into the quantum foam. And if you look closely, there's something beautiful about this mystery. It's a reminder that even the most powerful things, forces that shape worlds, can be soft-spoken. That gravity, the weakest of all, still commands the orbits of planets and the curvature of time. That the strong force, though confined to atomic nuclei, is the quiet heart of all matter. That the forces we overlook, like the weak interaction, are responsible for the fusion in stars, for the creation of the elements in your blood. Each force with its own personality, its own rhythm, its own whisper in the grand symphony of reality. So maybe the question isn't why they differ, but what their difference means. Maybe the universe isn't a machine built for simplicity. Maybe it's a poem, a structure built not only for function but for contrast, for complexity, for tension. And maybe the disparity of forces is like the difference between silence and thunder, between whisper and roar. Each needed, each meaningful, each part of a greater harmony we haven't yet fully heard. Because perhaps understanding isn't just about finding equality. It's about embracing difference, about learning why the weak force is weak and why that weakness matters, about recognizing that strength is relative, contextual, and often misunderstood. And that leads us back to you. to the human urge to seek pattern, explanation, closure. The desire to know why things are the way they are. It's this very curiosity that drives physics forward, that keeps telescopes pointed upward and equations scribbled deep into the night. And if the forces of nature still defy our understanding, if they still whisper secrets we haven't heard, it means the story isn't finished. It means there's more to discover, more beauty to unfold, more awe to feel. Because every disparity in nature is a doorway. Every imbalance is an invitation. And perhaps someday we'll find the unifying thread, the reason behind the quiet power of gravity, the fury of the strong force, the dual nature of electromagnetism, the elusive reach of the weak interaction. Or perhaps we won't. Perhaps we'll only get closer, never fully grasping, but always reaching. And maybe that, too, is by design. Maybe the universe isn't just made of forces and fields, but of questions. Questions that echo through the silence of space, waiting for someone, somewhere, to ask them well enough to hear the answer. Planck units, the smallest possible length, time, and mass. But why? There's something haunting about limits, boundaries beyond which you cannot go, no matter how hard you try. We encounter them in nature, in thought, in the fragility of the body and the ticking of the clock. But what if there existed limits, not imposed by fatigue or imagination, but by the very structure of reality itself? Not limits we eventually reach, but ones the universe itself refuses to cross. That's what physicists discovered when they stumbled upon what we now call the Planck units, the smallest possible measures of length, time, and mass that can ever meaningfully exist. Smaller than this, and reality begins to shatter. Measurement becomes meaningless. Physics collapses. It's as if nature whispered, "Here, but no further." And the more you look into these strange thresholds, the Planck length, the Planck time, the Planck mass, the more surreal the picture becomes. These aren't just small numbers. They are foundational boundaries, unseeable, unreachable, and yet somehow essential. So why do they exist at all? Why should the universe come with a built-in minimum scale? Why should there be a shortest possible length, a fastest possible tick of time, a mass that forms a dividing line between the quantum and the gravitational? What is the universe trying to tell us through these invisible walls? To begin answering that, we have to look at what the Planck units actually are. They're not numbers pulled from experiment. You can't build a ruler small enough to measure the Planck length, or a stopwatch fast enough to detect the Planck time. Instead, they emerge from mathematics, from the way three of nature's most fundamental constants interact. These are the speed of light, c, the gravitational constant, g, and Planck's constant, which governs quantum mechanics. If you combine these three in just the right ways, through dimensional analysis, you get quantities that define the Planck scale. The Planck length is about 1.616 x 10 to 35 meters. The Planck time is 5.391 x 10 to 44 seconds, and the Planck mass is 2.176 x 10 to 8 kilograms. These numbers are absurdly extreme. The Planck length is 100 million trillion times smaller than the nucleus of an atom. The Planck time is the time it takes light to travel that distance, effectively the universe's fastest clock tick. And the Planck mass, although small on human terms, is colossal for quantum particles. It sits strangely between the tiny particles of the quantum world and the massive objects that gravitation rules. It's in this tension, this intersection, of gravity, light, and quantum mechanics that the mystery lies. Because these units mark more than just smallness, they mark breakdown. Physics as we know it stops working at these scales. Below the Planck length, the very concept of space becomes meaningless. You can't say that something is here or there because there's no longer a defined structure of space to separate here from there. Likewise, at times shorter than the Planck time, causality becomes ambiguous. You can't be sure what happened first, or if cause and effect even hold. And at the Planck mass, something astonishing happens. If you try to pack that much energy into a quantum particle, it becomes a black hole. Think about that. Try to probe smaller and smaller scales with more and more energy, and suddenly, the universe shuts the door by collapsing space into darkness. You reach a point where your attempt to understand leads to erasure. And this is no ordinary erasure. It's a wall woven into the structure of existence. The Planck units aren't imposed by experiment or engineering. They are inscribed in the equations themselves, as if reality is telling us. Beyond this point, the questions themselves become ill-formed. It's hard not to feel something philosophical stir in the face of such boundaries. What does it mean for a universe to be discrete, to have a minimum scale beneath which reality dissolves? It means that space and time, as continuous and smooth as they appear to us, may actually be quantized, broken into indivisible chunks like the pixels of a cosmic screen. It means that beneath the illusion of flow and continuity lies a grainy, digital fabric where nothing is truly continuous. And this has staggering implications. It means there may be a smallest possible unit of distance, a shortest conceivable event, a pixelated texture of space-time that no microscope, no matter how powerful, can penetrate. It means that the universe has a resolution, and once you reach that resolution, everything blurs. Not metaphorically, literally. Your measuring stick ceases to measure. Your clocks cease to tick. Your concepts fall apart. And that's why Planck units matter. They are not just numbers. They are the edge of knowability. This is why physicists believe that to go beyond the standard model, to unify gravity with quantum mechanics, we must grapple with what happens at the Planck scale. Because that's where our greatest theories meet and clash. General relativity tells us how space and time bend, stretch, and warp under mass and energy. Quantum mechanics tells us how particles dance, tunnel, interfere, and blur. But these two theories speak different languages. They do not play well together. And at the Planck scale, they're both screaming over one another. To reconcile them, we need a theory of quantum gravity, a model that can describe black holes and particles, curvature and uncertainty, simultaneity and superposition. That's the Holy Grail, and it's hidden behind the wall of Planck units. String theory is one of the leading candidates for such a theory. It suggests that particles aren't point-like, but tiny, vibrating strings, whose different modes of vibration produce the variety of particles we observe. And in string theory, the Planck length plays a natural role. It's the typical length of a string. Below that, there's no meaning to smaller distances because strings can't be smaller than themselves. Loop quantum gravity, another approach, posits that space is made up of tiny loops woven into a spin network with discrete areas and volumes. Again, hinting that space itself is not continuous, but built from Planck-sized building blocks. Both theories, though wildly different, agree on one thing. The Planck scale is not just a measurement. It's a boundary between the known and the unknowable. But what if it's more than that? What if the existence of these limits isn't just mathematical? What if it's philosophical? What if the universe builds its rules not for convenience, but for coherence? A cosmos without limits would be chaotic, everywhere infinitely divisible, infinitely fast, infinitely dense. Nothing could form, nothing could stabilize. There would be no particles, no time, no memory. But with limits, with Planck boundaries, we get structure, we get meaning, we get a reality that can be explored, but not fully consumed. A reality that protects itself from total transparency. Perhaps the Planck scale exists not to limit us, but to sustain us, to provide the canvas on which reality can be painted without tearing. And maybe, just maybe, the deepest truths lie not in the infinities we chase, but in the boundaries we cannot cross. And so, in these tiny numbers, in these almost impossibly small units, lives a profound truth. that even the vastness of the cosmos has a flaw, that beneath every galaxy, beneath every particle, beneath every tick of time, there is a boundary where questions dissolve, where clarity gives way to haze, where language itself fails. And instead of being terrified by this limit, maybe we can be humbled by it. Maybe we can recognize that mystery is not a flaw in the universe, but its design. That not everything is meant to be known. Some things are meant to be stood before, like a silent mountain or a starlit sky, and simply respected. And maybe, when we reach the edge of what can be measured, what can be named, what can be reasoned, we'll find not emptiness, but stillness, not chaos, but symmetry. And in that stillness, in that final grain of space and time, maybe we'll finally understand that the smallest things often carry the greatest truths, not because they shout, but because they set the scale for everything else to sing in tune. The origin of mass. Higgs field helps, but doesn't fully explain. Imagine standing at the edge of a vast, empty desert with no wind, no sound, no movement. Just endless stillness stretching in every direction. Now imagine tossing a pebble into this silence and watching the ripples it makes. Not in sand, not in air, but in something more fundamental, the fabric of reality itself. This is what the universe felt like before mass existed. No atoms, no weight, no stars, no us. Just fields, humming invisibly through an empty stage. Among these, one field would change everything, giving rise to structure, to resistance, to substance. This field, called the Higgs field, has often been credited with answering one of the universe's most important questions. Why do things have mass? But here's the part we rarely confront. It's not the full answer. It's only part of a story that grows deeper, stranger, and more unsettling the closer we look. Because if the Higgs explains some of the mass we see, what explains the rest? Why do the very building blocks of reality behave as though they carry weight, resist, motion, and shape everything around them? Why does mass exist at all? To ask this is not just to ask why objects fall, it's to ask why anything is. Let's begin with the simplest image. Imagine you're walking through water. Each step takes more effort. You can move, yes, but you're being slowed down by something invisible but real. The Higgs field works in a similar way. It fills the universe like a field of molasses, and when particles like electrons move through it, they drag, acquiring what we call inertial mass, resistance to acceleration. This concept became a cornerstone of the standard model of particle physics, one of the most successful theories in science. The Higgs boson, discovered in 2012 at CERN, was the long-awaited proof that this field really exists. It was a triumph. And yet, it opened a deeper void, because only certain particles get their mass this way, and not even all of their mass. For example, the protons and neutrons in the nuclei of atoms, the things that make up most of the mass of the visible universe, get only a tiny fraction of their mass from the Higgs mechanism. The rest comes from somewhere else, somewhere deeper. To understand where, we have to dive into the realm of quantum chromodynamics, QCD, the theory of the strong force. Here, mass doesn't come from a field like the Higgs, but from the energy of motion and confinement. Picture this. Inside a proton, quarks whirl around at nearly the speed of light, bound together by gluons, the carriers of the strong nuclear force. These gluons don't just passively hold the quarks in place. They constantly exchange energy, snapping like rubber bands that refuse to stretch too far. And it's this energy, according to Einstein's famous equation, E=mc2, that gives rise to most of the proton's mass. Think about that. The mass of the universe isn't made of particles like marbles, but of tension, motion, and interaction. It's not about stuff, but about relationships between forces. And yet, even here, the mystery deepens, because we don't fully understand why this happens so precisely, so consistently, or why the Higgs field has exactly the properties needed to make the standard model work in the first place. The pieces fit, but we don't know why the puzzle exists. What makes this more haunting is that mass is what makes the universe feel real. Without it, particles would move at the speed of light, atoms wouldn't form, gravity would have no anchor to pull on. Time itself, defined by change, by inertia, would lose meaning. Mass gives the universe structure, gravity, and identity, and yet it comes from invisible fields, abstract forces, mathematical curiosities. It's as if reality itself is floating above a void of potential, held together by whispers we don't fully understand. The Higgs field may be a key, but it only unlocks one door. Behind it are corridors we haven't yet explored, questions we barely know how to ask. Why does the Higgs field exist at all? Why does it have a non-zero vacuum expectation value, allowing it to permeate space? Why does it couple to some particles and not others? Why do the coupling strengths differ, giving particles such wildly different masses? We call it spontaneous symmetry breaking. But even that term masks the reality that we have no idea why the symmetry breaks the way it does. It's like saying a mirror cracked, but not explaining who threw the stone. And this takes us to an even stranger place. Some physicists believe the Higgs field, and perhaps even the constants of physics that define mass, are not universal truths, but local conditions. That is, our universe may be one of many in a multiverse, each with its own values of mass, charge, and physical laws. In most of these, matter might not even clump together. Stars might never form. Life would be impossible. In this view, mass isn't a universal property. It's an accident, a cosmic lottery ticket. We live in a universe where the Higgs field happened to settle at the right value, allowing galaxies, stars, and people to exist. But that rightness has no explanation, at least none we've found. It could be chance, it could be necessity, it could be something stranger still, a hidden principle we haven't yet glimpsed, or a limit to our cognitive reach. This isn't just theoretical hair-splitting. It matters because mass isn't optional, it's existence itself. If the origin of mass is only partially explained, then so is the origin of everything you've ever seen or touched. Your body, your memories, your breath are bound up in this mystery. The chair you sit on, the gravity that holds you down, the time that ticks forward, all depend on mass behaving exactly as it does. And yet that behavior is built on unseen scaffolding, mathematical ghosts, unverified assumptions. The Higgs is real, yes, but it's not enough. It's the tip of a deeper iceberg, floating in an ocean of questions we don't know how to navigate. And as we build bigger colliders and chase higher energies, we're not just looking for particles, we're looking for meaning. Because to understand why mass exists is to understand why anything exists. And until we solve that, we are building our theories on foundations we cannot see. So maybe the real story of mass isn't about answers, but about humility. The Higgs field shows us that the universe is stranger than we ever imagined, but also more fragile. It reminds us that solidity is an illusion, that mass, weight, resistance, and presence all come from interactions we cannot touch, that we, ourselves, are made of fields, ripples in invisible oceans, dancing to equations we didn't write. And perhaps that's what makes it so profound, that something as mundane as mass, the thing that makes your hand heavy, your steps slow, your body present, is not simple at all. It is the result of hidden order, subtle imbalance, broken symmetries, and a kind of elegant violence in the fabric of space-time. It is not given, it is earned through interaction, through struggle, through compromise. And in that story, we may find echoes of ourselves, because we too are shaped by forces we don't fully understand. We too are made real by the invisible, and perhaps, just perhaps, understanding mass is a step toward understanding what it means to be something in a universe that could have been nothing. Why quantum spin has no classical analogy. Imagine holding a spinning top in your palm, watching it whirl effortlessly, defying gravity through motion and balance. You feel its weight, its direction. its resistance. You can see the axis around, which it turns, sense the gyroscopic stability, and, most importantly, you intuitively grasp its behavior. Now, imagine trying to describe a particle in the quantum world that also has spin, but that never rotates, has no axis, no surface, no moving parts. A particle whose spin isn't about rotation at all, but about an intrinsic property that exists without analogy in anything you've ever touched, seen, or felt. You can't imagine it spinning, yet it behaves as though it does. It has angular momentum, but no physical spinning. It obeys equations, yet defies all classical images. And the moment you try to reduce it to what you know, a turning sphere, a wobbling gyroscope, it slips through your understanding like smoke through fingers. This is the enigma of quantum spin. A property so fundamental to particles, yet so alien to the classical world, it challenges the very meaning of words like rotation or direction. And this contradiction isn't a side note in physics. It's a core pillar of how the universe works, including you. To understand just how strange this is, we have to first let go of our intuitions. In classical physics, spin is associated with something literally turning, like the Earth rotating around its axis or a basketball spinning on a fingertip. The faster it spins, the more angular momentum it has. You can stop it, reverse it, accelerate it, all within a visual, tactile framework. But when we move into the quantum world, those tools break down. Take an electron, for instance. It has a property called spin 1-2. That phrase alone is a clue to how weird things are. In our macroscopic world, spin is always a whole number, spin 1, spin 2, and so on. But a spin 1-2 particle doesn't need to rotate once to return to its original state. It needs to rotate twice. That's like twisting your wrist 360 degrees and not returning to where you started, needing a full 720-degree rotation to be reset. Try it. Your arm may not make sense of it, but the math does. This isn't a metaphor. This is literal behavior in the quantum domain. Electrons, quarks, and neutrinos all possess this trait, and it shapes how they behave, how they interact, and what kind of matter they can build. But even more bizarre, you cannot observe this spin directly. It's not a measurable direction of rotation, but rather a set of outcomes tied to probabilities, symmetries, and mathematical structures that don't resemble anything in our daily lives. In quantum mechanics, spin is encoded in something called a spinor, a mathematical object that doesn't live in ordinary space, but in a kind of abstract space that transforms differently from vectors. When you rotate a spinor 360 degrees, it doesn't come back to the same value. It picks up a negative sign. Only after 720 degrees does it return to its original form. This isn't just a quirk of math. It reflects something physically real about the particles we study. The Pauli exclusion principle, which states that no two fermions can occupy the same quantum state, arises because of spin. Without spin, 1-2 particles, matter as we know it couldn't exist. Atoms wouldn't be stable. Electrons would collapse into nuclei. Chemistry, biology, life, all would unravel. So here's the paradox. Spin isn't about spinning, yet it governs everything from the structure of atoms to the functioning of your brain. It's invisible, immeasurable in a classical sense, yet omnipresent and essential. It's like a ghost that moves the physical world, yet refuses to be seen on its own terms. Even more disturbing is how spin behaves when you observe it. In the quantum world, spin doesn't have a fixed direction until it's measured. An electron's spin can be up or down relative to a chosen axis, but before measurement, it exists in a superposition of both. It's not just that you don't know which one it is, it literally is both. Only when you measure it does the wave function collapse, forcing it into one state. But change the axis, and you change the meaning of up and down. It's not just the answer that's uncertain, the very question shapes the reality. Spin is contextual, and that context isn't metaphorical. It's built into the laws of quantum mechanics. The famous Stern-Gerlach experiment demonstrated this. Atoms with spin 1-2 pass through a magnetic field and split into two distinct paths, up or down. But change the orientation of the field, and the same atom splits differently. It's like tossing a coin and getting both heads and tails depending on how you look at it. This behavior isn't just puzzling, it's deeply non-classical. No spinning sphere can behave like this. No classical system can. Why does this matter? Because every electron in your body, every proton in every atom, every interaction in chemistry, every magnetic field you experience is influenced by quantum spin. MRI machines work by manipulating spin states. The stability of your DNA depends on it. The brightness of the stars relies on nuclear reactions governed by spin statistics. The universe itself, from the smallest particles to the largest galaxies, is scaffolded by a property that we can't see, can't touch, and can't explain using any classical analogy. It exists, it works, it's measurable in its effects, but not in its essence. And this is where the existential unease creeps in. Because if such a foundational piece of reality is inherently unvisualizable, then what does that say about the other things we believe we understand? How much of the world is really just comfortable metaphor, wrapped around unspeakable truths? How many of our beliefs are built not on clarity, but on coping? Some physicists have tried to bridge the gap. They speak of spin as an angular momentum, vector of symmetry groups like SU2 and their double covers, of Dirac matrices and quantum fields. But these are not bridges to classical understanding. They're signposts to a deeper terrain, one we cannot walk with ordinary shoes. They reveal that spin is not derived from anything simpler, it is fundamental. It's a property not of motion, but of identity. Two electrons are identical because they have the same spin, the same intrinsic quantum numbers. And this sameness isn't reducible, it just is. That's what makes quantum spin such a uniquely jarring concept. It doesn't ask for comparison, because no comparison exists. It simply declares, I exist this way, understand me if you can. And so, we return to our metaphorical top. Only now, we realize it was a distraction all along. There is no top. There is no spinning. There is only the abstract, the hidden, the non-classical logic of the quantum world. And yet, it moves us, shapes us, defines us. The electron spin isn't just a property, it's a signature, a truth, etched into the code of reality. It resists analogy because it was never meant to be understood through analogy. It exists outside our intuition, not because it's broken, but because it's deeper. It tells us that the universe is not built to be visualized. It is built to be measured, felt, experienced indirectly through mathematics, through experiment, through wonder. And that may be its greatest lesson, that reality does not owe us comprehensibility, that we too must spin again and again through cycles of learning, confusion, and awe before we begin to glimpse even a fraction of what it truly means to exist. What sets the speed limit of light? It's constant, but why this value? Imagine trying to paint a sunset while the sun keeps racing away from you at a speed you can never catch. No matter how fast you run, how far you reach, the horizon stays, just out of reach. Now imagine that every single thing you've ever seen, every color, every face, every memory, is made of that sunset light. But the strangest part isn't that light moves. It's that it always moves at the same speed, regardless of where you are or how fast you're going. Light, the very thread from which your reality is woven, does not bend to your perspective. It doesn't slow down or speed up based on your chase. It holds its own pace, 299,792,458 meters per second. No more, no less. But why that number? Why not slower or infinitely faster? Why does the universe insist on this speed limit? This isn't just a question for physicists. This is a question that strikes at the very heart of how we understand time, causality, and our place in the cosmos. Because buried within that number is a cosmic decision. a design, a boundary, one that doesn't just govern light, but everything. And if you sit with this fact long enough, it begins to whisper something quietly unsettling. The universe has rules, but it doesn't owe you reasons. To begin unpacking this mystery, we need to first realize how unnatural the speed of light actually is, not because of its magnitude, but because of its constancy. In our everyday world, speed is relative. A car speeds up, a train slows down, the wind shifts, sound echoes differently in air than in water. But light doesn't care. Whether you're standing still or flying in a spaceship near the speed of light, if you measure a beam of light moving past you, it always travels at the same speed. Einstein realized this wasn't just a mathematical quirk, it was a fundamental law, and it led him to shatter centuries of assumptions with special relativity, a theory in which time slows, lengths contract, and simultaneity becomes subjective, all to preserve this one bizarre truth that light has a fixed speed in a vacuum. But what sets this speed? Is it a brute fact of nature? Is it derived from deeper constants? Or is it, more chillingly, just a number the universe picked without explanation, just as a coin might land on heads? To answer this, we have to peer into the fabric of space and time itself. Light is an electromagnetic wave, an oscillation of electric and magnetic fields. James Clerk Maxwell's equations, crafted in the 19th century, showed that when you let these fields dance freely, they produce a wave that moves at a speed determined not by choice, but by two constants: the vacuum permittivity and vacuum permeability. These constants are properties of empty space, the very vacuum between particles. When you plug them into Maxwell's equations, you don't guess the speed of light, it emerges. Like a melody arising from the tuning of two strings, the universe hums with a specific frequency. But this only shifts the question: why are those constants what they are? Why does empty space have just the right stiffness and elasticity to allow light to travel at that speed and no other? It's like discovering that the walls of your house are vibrating, not randomly, but at a perfect pitch. Someone or something has tuned the room, and that tuning runs deeper than most realize. The speed of light isn't just about light. It defines the structure of causality in the universe. It's the maximum speed at which information, matter, or influence can travel. It sets the boundary for cause and effect. If something could exceed this speed, paradoxes would arise. Effects would precede causes, timelines would loop, reality would break. A message sent faster than light could arrive before it was even written. The very fabric of what we call reality would unravel. So perhaps, in that sense, the speed of light isn't just a speed. It's a defense mechanism, a firewall that guards the timeline of the cosmos. It tells you, this far, no further. This is the limit beyond which meaning collapses. But why does that firewall sit exactly at 299,792,458 meters, not 300 million, not 100 million? That level of precision seems almost artful, as if nature didn't just draw a line, it carved it in stone with a scalpel. Modern physics has tried to go deeper still. In natural units, physicists often set the speed of light, c, to 1. Not because it's irrelevant, but because it's so fundamental. It's like measuring distance in units of distance itself. In this formulation, what matters is not the value of c, but the relationships between c and other constants, like Planck's constant h, or the gravitational constant g. When you combine these, you get Planck units, the natural scales of time, length, mass, and temperature in the universe. But even here, the mystery remains. These units are derived from constants that we measure, not deduce. They are empirically observed, not logically inevitable. So even in the deepest caves of theoretical physics, we find no torch that illuminates why light travels at the speed it does. We only know that if it didn't, the universe would be a radically different place. Think of the implications. If the E speed of light were just slightly slower, stars might burn differently, planets might not form, time might flow in strange ways. The evolution of life, the possibility of chemistry, the very stability of atoms, all depend, directly or indirectly, on C. And yet, nowhere in the laws of physics is this value explained. It is used, assumed, built upon, but never justified. This is perhaps the most humbling truth in all of science, that the foundations of our reality are not necessarily built on logic, but on consistency. The universe works as if light must move at this speed, but it does not tell us why. We are left, as always, staring at the equation like a child stares at a locked door, knowing there's something beyond it, but not knowing how to knock. And here's where things turn philosophical. Because if light had a different speed, then everything, including you, might be different. Your thoughts, your heartbeat, the size of your body, the rate at which you age, the way you remember love or grief or wonder, all scale with the fabric of space-time. You're not just in the universe, you are a rhythm set to its beat. And that beat, the cosmic metronome, is light. Every time you look at the stars, you're seeing the speed of light written across the sky. Every second you live is measured against how far light travels in a vacuum. Every word you read, every breath you take, every neuron that fires in your brain is synchronized, silently and unknowingly, to C. So maybe the better question isn't, why is the speed of light what it is? Maybe the question is, what would it mean if it were different? Would there be thought, memory, physics itself? Or would reality collapse into a chaos we can't imagine? Maybe this constant isn't just a fact of physics, it's a precondition for existence. Not just for life, but for coherence itself. Maybe it's not that the universe is built on logic, but that this one number allows logic to even exist. Maybe the speed of light is the one thread holding the tapestry together, taut and unwavering. And maybe, just maybe, we are lucky enough to live in a universe that chose such a thread and stitched us into it. The proton radius puzzle. Why protons change size? Depending on how you measure them. Imagine trying to measure the heartbeat of the universe with a ruler made of fog. Every time you place it down, it shifts. Every time you look closer, the lines on the ruler blur. You reach again, recalibrate, hold your breath, but the answer dances just beyond your grasp. Now imagine that what you're trying to measure isn't a galaxy or a black hole or something hidden in the edges of space. It's the proton, one of the fundamental building blocks of everything you know. It sits at the core of every atom in your body, in every breath you take, in every star you've ever wished upon. And yet somehow, this most familiar particle has become one of the greatest mysteries in modern physics. Not because we don't know it exists, not because we can't find it, but because we can't seem to agree on how big it is. The proton, the stable heart of hydrogen, changes size depending on how you look at it. And this simple yet maddening inconsistency has cracked open a door to something far deeper, a flaw in our measurements perhaps, or maybe, just maybe, a crack in reality itself. To understand this puzzle, we must return to the most precise tools science has to offer: spectroscopy and scattering. When scientists first tried to measure the size of the proton, they did so using electron scattering. This is a method where high-energy electrons are fired at protons, and from the way those electrons deflect, physicists infer the spatial spread of charge inside the proton. Think of it like throwing marbles at a cloud and deducing the cloud's shape from the marble's paths. Using this method, over decades, scientists consistently landed on a value for the proton's radius, about 0.877 femtometers. But in 2010, a revolutionary new experiment changed everything. Instead of using electrons, scientists used muons, heavier, cousins of the electron, to probe the proton via monic hydrogen spectroscopy. The result? A proton radius of just 0.840 femtometers. A difference so small it seems laughable, until you realize that in the realm of fundamental physics, this was a catastrophe. This wasn't a minor discrepancy. It was a full-blown contradiction, the kind that should not exist. This clash, this conflict between electron-based and muon-based measurements became known as the proton radius puzzle, and it sent shockwaves through the physics community. Were our models wrong? Were our instruments flawed? Was the discrepancy a result of systematic error, or was it whispering something deeper, a hole in the standard model itself? Some physicists began to ask bold questions. Could it be that muons interact with protons differently than electrons do, not because of mass or error, but because of a fifth fundamental force? Could the laws of physics be subtly different for particles we thought were nearly identical? Could the universe be hiding layers of structure, folding truths beneath folds like origami, waiting for the right type of particle to reveal them? To most people, the size of a proton changing by 4% seems trivial, inconsequential. But in the high-precision world of particle physics, this is like discovering a ticking sound behind the wall of a vault you thought was silent. It's not the size of the crack that matters. It's the implication that something behind the wall might be moving. The Standard Model, our most successful theory of particles and interactions, is exquisitely tuned. It explains almost everything we see, and yet it has always felt incomplete. It can't explain dark matter, or gravity, or the accelerating expansion of the universe. And now, staring at the proton, we're forced to ask, what if it can't even explain itself? Attempts to reconcile the discrepancy flooded in. New theoretical calculations, reanalysis of data, alternative experimental setups. Some blame the difference on quantum electrodynamics, QED corrections being misapplied. Others suggested that maybe muons feel extra forces, perhaps involving hypothetical particles like leptoquarks, exotic mediators between quarks and leptons that lie beyond the Standard Model. If true, this would be seismic. It would suggest new physics, uncharted forces, hidden symmetries, or unknown particles tugging subtly at the edges of matter. But others urged caution, reminding the community that extraordinary claims require extraordinary evidence. Maybe the measurements were flawed. Maybe there were unknown biases in how we model interactions at these energy scales. Maybe reality wasn't cracking. Maybe we just weren't measuring carefully enough. Still, the fact remains, if two different tools give two different truths, then we must examine not just the tools, but our entire framework for truth. Science, after all, doesn't just collect data, it interprets it. An interpretation is built on assumptions, models, approximations. What if our assumptions are off by a hair, and that hair is all it takes to obscure the true shape of a proton? In this sense, the proton radius puzzle becomes more than a technical discrepancy. It becomes a mirror reflecting our limits. It asks, how much do we truly know about the particles we take for granted? And how much of that knowledge is built on layers of inference, stacked like cards in a tower, stable only if each assumption holds? The implications spiral outward. If protons behave differently under different probes, then so might other particles. Perhaps this isn't a proton problem at all. It's a symmetry problem, or a problem of interaction hierarchy, where particles reveal different properties depending on who's asking the question. Just like a person might act differently under scrutiny from a stranger versus a loved one, maybe particles too shift subtly under the gaze of electrons versus muons. This idea, radical as it sounds, taps into something more poetic: the observer's role in defining the observed. A foundational idea in quantum mechanics, now resurfacing at the subatomic level in an unexpected way. And yet perhaps the most haunting possibility is this: we might never know why. Not because the truth isn't out there, but because our methods, our particles, our limitations may forever obscure it. Perhaps the proton's true radius is not a fixed number, but a contextual reality, something that depends on the dance between energy, measurement, and interpretation. A shape that warps under pressure, a number that shifts like a shadow under different lights. In this view, the universe isn't lying to us. It's just complex beyond our models, a symphony of particles that doesn't play to our sheet music. Today, new experiments continue. The CREMA collaboration has extended its measurements. Other labs have tested both electronic and muonic hydrogen again and again. Some results seem to agree with the smaller radius, others support the larger one. The mystery remains unresolved. But perhaps that's the point. Perhaps mysteries like this aren't failures, they're invitations. Invitations to look deeper, to think differently, to ask bigger questions. The proton radius puzzle is not just about a tiny particle. It's about the limits of certainty, the texture of reality, and the breathtaking possibility that the universe still hides secrets in the things we thought we knew best. The missing baryon problem, half of ordinary matter, was just recently found. What if I told you that for decades, half of everything you thought existed didn't? Not metaphorically, not in some philosophical thought experiment, but in the cold, stubborn arithmetic of the universe, where mass must be accounted for like money in a vault. Now imagine standing in a room filled with furniture, lights, people, and air, but only being able to see half of it. You reach for a chair, and your hand passes through it. You hear someone speak, but the voice comes from nowhere visible. Everything you trust, sound, touch, light, is suddenly incomplete. That's what cosmologists have felt for nearly half a century. They weren't looking for dark matter or dark energy, the shadowy titans that dominate our cosmos in mystery and scale. No, this was about ordinary matter, the kind that makes up stars, planets, oceans, and you. Baryonic matter. The protons and neutrons forged in the fires of the Big Bang, woven into every strand of your DNA, suspended in every drop of water. And yet, for the longest time, we simply couldn't find half of it. It was missing, vanished, gone without explanation. A cosmic vanishing act that defied everything we thought we knew about the fabric of the universe. And the story of how we finally found it, how we pulled it from the void, is one of the most haunting, humbling, and miraculous discoveries in modern science. To understand what went missing, you first need to grasp what should have been there. After the Big Bang, the universe cooled, and protons and neutrons, collectively known as baryons, formed in vast quantities. Precision measurements of the cosmic microwave background, relic light from the early universe, combined with models of nucleosynthesis, told us exactly how much normal matter should exist. These weren't guesses. These were measurements with decimal point confidence. And yet, when astronomers looked out into the cosmos, adding up every galaxy, every cluster, every hot cloud of gas visible in X-ray, they could only account for about 50% of the expected baryonic matter. Half of the universe's ordinary matter was simply unaccounted for. It wasn't dark matter. It wasn't some exotic form of unknown physics. It was regular matter, the stuff you can theoretically touch, weigh, and see, missing without a trace. This haunting mystery became known as the missing baryon problem, and it lingered like a stubborn echo through every calculation, every simulation, every telescope pointed at the heavens. Some thought maybe the matter had been swallowed by black holes. Others speculated it was locked away in dim dwarf galaxies, or spread so thin it escaped detection. But as observations became sharper, the gap remained. Half the universe's baryons were nowhere to be found, and the longer they remained missing, the more fragile our models became. Because if we couldn't find what we were absolutely sure should exist, how could we ever hope to find what we weren't sure about at all? Then came a quiet revolution. A new generation of astronomers started to look between the galaxies, in the cosmic voids where light rarely dared to travel. What if the missing baryons weren't gone, but diffuse? Spread like mist between clusters, and filaments, too cool to glow brightly, too hot to be seen in traditional optical surveys, too thin to leave obvious fingerprints. They searched for whispers in the silence, faint distortions in the light of distant quasars, subtle X-ray signals from diffuse gas, spectral fingerprints only visible when you added up hundreds of signals from across the sky. It was like trying to hear a whisper in a storm, possible only if you knew exactly where to listen and how to listen together. The breakthrough came when teams used a method known as the Sunyaev-Zeldovich effect, which examines how cosmic microwave background photons gain energy as they pass through hot gas. By stacking data from thousands of galaxy pairs, researchers detected a web of hot, diffuse gas, a filamentary structure threading between galaxies, known as the warm-hot intergalactic medium, or WIM. This gas was not invisible, but it had been overlooked, hiding in plain sight because we weren't looking for it the right way. It didn't cluster like stars. It didn't glow like nebulae. It drifted between, stretched across millions of light years, like the ghost of the cosmos. And just like that, we started finding the missing half, not all at once, but piece by piece. By 2020, research teams confirmed that nearly all of the previously missing baryons had been detected, lingering in this diffuse web of cosmic threads. The WIM wasn't bright, it wasn't flashy, but it was there, patient, persistent, present, all along. The ordinary matter we were sure had vanished wasn't missing, it was merely invisible to the tools we trusted most. And that simple truth, more than any equation or telescope, changed everything. Because it reminded us that the universe doesn't bend to our instruments. It doesn't care what we expect or what we want. Reality is not obliged to reveal itself on demand. There's a humility in this discovery that lingers far deeper than the physics. It whispers something haunting to anyone, willing to listen. How many other truths are out there, quietly existing, just outside the range of our perception? How many answers do we already have, hidden in data we dismiss, in corners we never thought to illuminate, in patterns we haven't learned to see? The missing baryons were never truly gone, but their absence taught us to search better, to question harder, to listen to the silence between the signals. The discovery of the WIM wasn't just a triumph of detection, it was a moral lesson in cosmic patience. And yet, even as this chapter closes, it opens new questions. What role does this vast intergalactic mist play in the evolution of galaxies? How does it interact with dark matter? Could its movements explain discrepancies in the large-scale structure of the cosmos? Could it be the medium through which cosmic magnetism pulses, or even the bridge between ordinary and dark matter? The WIM is no longer missing, but it's still mysterious. And now that we've found it, the real work begins. Because the universe doesn't just hide things, it layers them, and every veil you lift reveals a deeper shadow. In the end, the missing baryon problem was never about the baryons. It was about us, our assumptions, our blind spots, our belief that reality should conform to the limits of our vision. It reminds us that not all absence is non-existence, that sometimes things are hidden not because they are far away, but because we never thought to look where they actually are. And if half the universe's ordinary matter could elude us for decades, what else might still be waiting just beyond the reach of our current imagination? The magnetic monopole, a particle that should exist, but we've never seen. Imagine finding half of a magnet lying on your desk, a single, solitary north pole, with no south to complete it, like a soul without a shadow, a question without an answer. You turn it over in your hand, expecting the familiar tug, but it never comes. It's not broken. It's not part of something larger. It's complete, alone, whole, and yet it shouldn't be, because everything you've ever learned about magnets says they come in pairs. Split a magnet in half, and you don't get a monopole. You get two smaller dipoles, each with a north and south, like splitting fire only to find more flame. But in the hidden symmetries of the universe, in the mathematics that governs everything, from the birth of stars to the flicker of neurons, there is a peculiar absence, a missing piece, a silent echo, the magnetic monopole, a particle so elegant, so necessary that it should exist, but never has. Not in any detector, not in any particle collider, not in the vacuum of space or the bowels of the Earth. It is a ghost written into the laws of physics, a phantom that completes an equation, but escapes the world, and its absence is not a trivial oversight. It is a cosmic riddle that gnaws at the symmetry of existence, whispering that something fundamental, something beautiful, is missing from our picture of reality. To understand why the magnetic monopole matters, you first have to appreciate the profound balance that defines electromagnetism. Electricity and magnetism are two sides of the same coin, unified by Maxwell's equations, inseparable in their dance. A moving electric charge creates a magnetic field. A changing magnetic field induces an electric current. It's a relationship of symmetry, reciprocity, and grace. And yet, there's a tension in this symmetry. We have electric monopoles, isolated charges like electrons and protons, but no magnetic counterparts. There are no solitary north or south magnetic charges. Magnetism is always dipolar, always dual, as if the universe insists on coupling what it cannot unbind. And that seems strange. Why this imbalance? Why this asymmetry in a universe so obsessed with symmetry? The math doesn't forbid monopoles. In fact, it craves them. If a magnetic monopole existed, even just one, the beauty of Maxwell's equations would be restored to a deeper symmetry. The equations would mirror each other. The roles of electric and magnetic fields would become completely interchangeable. Nature would become, in a sense, more complete, more whole. And the implications wouldn't stop there. The very existence of magnetic monopoles would explain why electric charge is quantized, why electrons and protons always carry exactly the same amount of charge, no more, no less. The fact that the universe speaks in discrete units of electric charge is a mystery in itself. But the presence of even a single magnetic monopole would mathematically necessitate that quantization. It would transform a weird coincidence into a necessary law. That's the kind of beauty physics rarely offers. One particle to explain one of the deepest puzzles in nature. And yet, we've never found one. Decades of searching, scouring cosmic rays, combing through the wreckage of high-energy collisions, scanning the deep rock of ancient Earth, have yielded nothing. Not a single track, not a single signal, nothing. It's as if nature is teasing us with a perfect idea it refuses to manifest. And that tension, that haunting absence, raises a profound question. Why write something so perfect into the laws of reality if you never intend to make it real? Some physicists think the monopole once existed in the earliest fractions of a second after the Big Bang, when temperatures and energies were high enough to birth exotic particles. According to grand unified theories, guts, magnetic monopoles should have formed abundantly in that cosmic furnace. But if they did, where are they now? One answer comes from cosmic inflation, the rapid expansion of space that occurred just moments after the Big Bang. Inflation, like a magician sweeping a cloth over a table, would have spread out those monopoles across the universe, diluting them to the point where finding one now would be like spotting a single grain of sand in all the oceans of Earth. They might still be out there, floating, waiting, rare beyond comprehension. Others suggest they're hiding in plain sight, that our detectors are looking for the wrong signature, that we've misunderstood what a monopole might be, that it's not a fundamental particle like an electron or quark, but an emergent entity, a collective excitation in exotic materials, a byproduct of symmetry breaking in the quantum vacuum, a ripple in some hidden dimension. In recent years, scientists have even created quasi-particles in laboratory systems, such as spin ice materials, that behave like magnetic monopoles. These aren't true monopoles, but they mimic the behavior, like shadows cast by something deeper. Are these hints, echoes, or just playful coincidences from nature's bag of tricks? But perhaps the most haunting possibility is that monopoles don't exist at all, not because they can't, but because the universe chose not to include them. That in the vast space of what's mathematically possible, reality picked a path of asymmetry, that we live in a universe where elegance was available but not selected. And that possibility forces us to reconsider how we think about physical law. Are the laws of nature written in stone, like commandments, or are they emergent, selected by cosmic chance, shaped by initial conditions, born from a deeper layer of randomness we have yet to understand. In many ways, the magnetic monopole is more than just a missing particle. It is a symbol of our hunger for symmetry, our yearning for completion. It represents the ideal that nature should be beautiful, balanced, and whole, that every question has an answer, every force a partner, every duality a unification, but nature isn't obligated to fulfill our aesthetic dreams. Sometimes it writes half a poem and leaves the rest blank. Sometimes it leaves the puzzle unfinished, the symmetry broken, the particle unmade. And yet, we search. Because the absence of the monopole is a kind of presence, a silence that demands explanation, a hole in the map that tells us the map is incomplete. And in that absence, we are reminded that physics is not just about what we see, but what we fail to see, what eludes us, what haunts the edges of theory and observation. The magnetic monopole, whether it exists or not, has already shaped our understanding. It has pushed us to refine our equations, build new detectors, reimagine the early universe. Its non-existence is an active force in our science. So maybe the magnetic monopole isn't lost. Maybe it's waiting for the right tool, the right eye, the right question. Or maybe it already passed us by, unrecognized, unmeasured, drifting through the vast silence of space. And maybe, in chasing it, in trying to grasp the ghost of a particle that completes the poetry of nature, we'll discover something even deeper, that the universe does not owe us beauty, but that beauty can still emerge from the broken lines, the asymmetries, the empty spaces between what is and what should be. The speed of gravity. We know it exists, but not exactly how it travels. What if I told you there's a force that binds the galaxies, that keeps the Earth spinning in its gentle rhythm around the sun, that holds the moon above us and whispers to the tides, but that this very force, the one you've trusted your entire life to never fail, might not move as quickly as you think? That gravity, the oldest companion of our existence, might not even work the way we imagine. Imagine dropping a ball from your hand, watching it fall, and realizing that the force pulling it downward didn't reach it instantly, but arrived late, like a message delayed in a cosmic post. It sounds absurd. Gravity, slow, but the more we probe into the heart of the cosmos, the more this ancient force starts to look like a puzzle whose edges don't quite match. It's there, undeniably real. We see its pull, feel its weight, track its influence. But how it travels, and how fast, remains one of the strangest and most quietly unnerving questions in physics. And in that uncertainty lies something deeply human, because if even gravity has secrets, then what else have we mistaken for truth simply because we felt it? For centuries, gravity was thought to be instantaneous. Newton imagined it as a kind of invisible tether connecting every object in the universe. The Earth pulls on the moon, the sun pulls on the Earth, and every star in the sky pulls on every other, no matter how far apart. It was elegant, simple, but also strange. Because if gravity acts instantly, then it must somehow know, right now, where everything is. That would mean information travels infinitely fast, faster than light, violating the cosmic speed limit set by Einstein. And so, with the birth of relativity, gravity changed. It was no longer a force that leaped across space, but a curvature, a warping of space-time itself. In this new view, massive objects bend the fabric of reality, and other objects follow those curves, like marbles rolling along a warped sheet. And changes in that curvature, ripples from a star collapsing, or two black holes colliding, propagate through the universe not instantaneously, but as waves, gravitational waves. But here's the problem. Knowing something exists isn't the same as understanding how it behaves. We know gravity travels because we've seen those waves. In 2015, LIGO detected the tremble of space-time from colliding black holes more than 1 billion light-years away. It was a whisper from the dark, a subtle quake in the cosmic sea. And from the timing of those waves, scientists could estimate that gravity moves at or near the speed of light. But near is the key word, because in physics, almost is never enough, especially when you're dealing with the foundations of the universe. The truth is, we don't know with absolute certainty whether gravity moves exactly at light speed. We know it's close. But how close? And does it always move that way? What if gravity is more subtle than we thought? Not a fixed speed signal, but a phenomenon with context, nuance, even moods. Could gravity have layers, like a conversation, spoken in different tones? Could its speed change in extreme conditions? Near black holes, during the Big Bang, in the quantum foam beneath reality? These aren't idle questions, because if gravity moves slower than light, it opens the door to contradictions, or possibilities, or both. Let's follow a thought experiment. Imagine the sun vanished right now, snuffed out by some cosmic trick. Light from the sun would continue for 8 minutes before darkness reached Earth. But what about gravity? If gravity also travels at light speed, Earth would continue in orbit for 8 minutes, then spiral off. But if gravity were instantaneous, Earth would feel the change before the light disappeared, a violation of causality. And if gravity was slower than light, Earth would spiral off after the sky went dark. The timing matters, because it's not just a test of gravity, it's a test of reality's consistency. So far, the evidence suggests gravity moves at light speed, but all of our data is indirect. The events we've observed, the collisions of black holes or neutron stars, are rare, complex, and buried in noise. Extracting the speed of gravity from those signals is like trying to measure the speed of a whisper during an earthquake. And there's another wrinkle. We don't actually know what gravity is. Is it a particle, a wave, a field, a geometric illusion? If it's a wave, then it should have a speed. If it's a particle, a graviton, then that particle must be massless to move at light speed. But we've never detected a graviton, not even a hint. And without that detection, we're guessing. Beautifully, brilliantly, but still guessing. Some physicists suggest that gravity might not even be a fundamental force, that it could be emergent, rising from something deeper, like temperature emerges from the random motion of molecules. In these models, gravity isn't a thing, but a shadow of something else. And if that's true, then its speed might be the wrong question. You can't ask how fast a shadow moves. It depends on what's casting it and how the light changes. Likewise, gravity might not travel in the traditional sense. It might ripple, stretch, curve, not through space, but as space. And then there's quantum mechanics, the great thorn in gravity's side. Because every other force in nature, electromagnetism, the strong and weak nuclear forces, has a quantum theory, a framework that explains its behavior at the smallest scales. Gravity doesn't. After decades of work, we still don't have a quantum theory of gravity. String theory, loop quantum gravity, emergent gravity, each offers ideas, none offers proof. And without that theory, we can't predict how gravity behaves at the Planck scale, the realm of the unimaginably small. It's like trying to understand music without knowing what a note is. And here's the paradox. Gravity is the weakest force in nature. A fridge magnet can lift a paperclip against the pull of the entire Earth. And yet gravity dominates the cosmos. It shapes galaxies, bends light, dictates the fates of stars. Why? Because it has infinite range. It never shuts off, and it affects everything with mass and energy. But its weakness might be the reason we can't pin down its speed. Gravitational. Waves are incredibly faint. Detecting them is like trying to hear a leaf fall in a hurricane, and yet we do, which means we're close. But close isn't understanding, and so we wait. We build better detectors, we model better theories, we stare into the void, listening for whispers, and in that waiting, we confront something more profound than any speed or equation. We confront our own assumptions, that we know what gravity is, that we understand how the universe works, that reality follows rules we can write down. But what if those rules are just approximations? What if gravity isn't slow or fast, but deeper? There is something haunting about a force that moves the universe, yet refuses to show us how. Something poetic about a pull we all feel, but cannot follow. Gravity doesn't glow, it doesn't shout, it doesn't carry charge or color. It simply bends, quietly, invisibly. And in its silence, it tells us a story, not of certainty, but of mystery. A story in which the very concept of speed might be too shallow, in which motion, causality, and connection take on meanings we've barely begun to grasp. So the next time you feel your weight, remember, that pull isn't just a force, it's a question. It's a signal sent across the fabric of space-time, a message from the mass of the Earth to your body, and the speed of that message might be the speed of light, or it might be something stranger, something older, something we haven't yet dared to name. The Pioneer Anomaly. Spacecraft slightly slowed for no clear reason. Imagine sending a message in a bottle into the vast black ocean of space. A fragile metal emissary carrying not only instruments and data, but the hopes of a species daring to reach beyond its cradle. The Pioneer 10 and 11 spacecrafts were such messages. Launched in the early 1970s, they were humanity's first attempts to step outside the solar system's familiar shores. They flew past Jupiter and Saturn, capturing images and readings never before seen. And then they kept going, farther than anything we had ever built. But as they drifted into the silence between stars, something peculiar began to happen. Something so subtle, so slight, that it might have gone unnoticed, if not for the meticulous minds tracking their journey. The spacecrafts were slowing down, just a little, but enough to matter, enough to make us question whether we truly understand the space they were traveling through. This wasn't a mechanical failure or a calculation mistake. It was a whisper from the edge of physics, and it still hasn't been fully explained. The anomaly appeared in the form of a tiny, consistent acceleration toward the Sun, about 874 some 10 × 10 meters per second squared. That's less than the width of a human hair gained in velocity every second. So small that it would seem trivial, but when you're navigating the vast distances of interstellar space, when precision is everything and every signal is timed with atomic clocks, even a nudge that's slight becomes a mystery worth unraveling. And as engineers and physicists poured over telemetry data from Pioneer 10 and 11, they found that this deviation wasn't random. It was persistent and unexplained. The spacecrafts were veering ever so gently off course, not enough to alarm, but enough to haunt. At first, the assumption was straightforward. There must be some thermal emission from the spacecraft, heat radiating unevenly, creating a recoil effect, like a photon-based thruster gently pushing against the vacuum. Spacecraft generate heat as their electronics operate, and if that heat escapes more in one direction than another, it can create a force. This explanation seemed promising, elegant even. But the models weren't consistent. The numbers didn't fully line up. Some estimates suggested thermal recoil could explain part of the anomaly, maybe most of it, but not all. And that's where the problem deepened, because science, when honest, lives in the margins, and the margin left unexplained was enough to keep the anomaly alive. Some suggested gravitational influences from the Kuiper belt, a disk of icy bodies beyond Neptune. Perhaps there was more mass out there than we thought, pulling subtly on the spacecraft. But that too failed to account for the pattern of deviation. Others speculated about dark matter, invisible mass permeating space, affecting the Pioneer's path like a faint wind against a drifting feather. Still others proposed modifications to Newtonian gravity, that maybe at great distances, gravity behaves differently, that perhaps there are aspects of motion we've only just begun to glimpse, that perhaps space itself isn't as empty as we believed, and in that last suggestion lies something profoundly unsettling. Because the Pioneer anomaly isn't just about a spacecraft veering slightly off course. It's about what that deviation implies. It hints at the possibility that our current models of physics, our most trusted equations, may be incomplete, that the elegant latticework of Newton, Einstein, and quantum mechanics might have overlooked a whisper. And that whisper came from two quiet travelers leaving home. But the anomaly also carries a human story. These spacecraft weren't just instruments, they were symbols. On board Pioneer 10 was a golden plaque, a message from Earth, etched with the outline of a man and woman, a diagram of our solar system, and instructions in the language of mathematics on where to find us. It was a gift to the unknown, a declaration of presence. And it was that same craft, years later, that gave us a riddle we still haven't solved. It's poetic in a way. We sent a message to the stars, and the stars whispered something back, not in words, but in physics. As the years passed and the spacecraft grew more distant, the signals became fainter, harder to interpret. Pioneer 10's last transmission was in 2003, a ghostly echo from the edge of interstellar space. Pioneer 11 had stopped even earlier. Their power was fading, their instruments cold. But the data they sent continued to stir debate. Scientists published papers, argued at conferences, built models, and ran simulations. Some declared the mystery solved, citing refined thermal models. Others insisted that something deeper remained, a crack, a flaw, a window. And here we find ourselves, decades later, still wondering, still chasing a tiny drift in a distant craft. And isn't that the essence of exploration? That we're willing to chase a question through the dark, across billions of kilometers, because we believe that even the smallest deviation might hold a key, that a hair's breadth of uncertainty is enough to make us rethink the cosmos. Because if gravity needs adjustment, if the vacuum has hidden forces, if the fabric of space-time carries friction or drag, even minutely, then everything changes. Our understanding of galaxy formation, cosmic inflation, black holes, dark energy, all of it depends on gravity behaving as predicted. And yet two ancient probes hint that maybe, just maybe, it doesn't. We stand at the intersection of certainty and mystery. On one side, the confidence of physics, built over centuries, tested in accelerators, confirmed in space. On the other, a whisper from a dying signal across the stars. And in between, the Pioneer anomaly, a stubborn, quiet deviation that refuses to go away. Some mysteries fade with time, others deepen. The Pioneer anomaly has done both. It no longer headlines journals. It doesn't shake the foundations the way it once did. But beneath the surface, in the laboratories of gravitational theorists and the notebooks of curious students, it remains a riddle, a reminder that the universe is bigger than our equations, and that sometimes the most important answers come not from what we expected, but from what we almost missed. So when you look up at the night sky and see a pinpoint of light, remember that out there, in that silence, two machines drift alone, carried by momentum, guided by laws, but touched perhaps by something more, something we don't yet understand. Their path is a question, their signal, a hum in the void. And the anomaly they revealed? It is not an error, it is an invitation to look closer, dig deeper, and never assume we've reached the end of what reality has to teach us. The universality of free fall. It always works, but no one knows why. Imagine if you woke up one morning to find that gravity had suddenly changed its mind, that the fundamental force that has governed the universe since its birth was no longer consistent. What if some objects began to fall faster, some slower, and others simply refused to fall at all? The world you knew would dissolve into chaos. Airplanes soaring across the skies might unexpectedly lose lift and plummet earthward. Bridges and skyscrapers under construction could twist, buckle, or collapse without warning, defying every calculation engineers have painstakingly made. Even the most mundane actions, walking down the street, dropping a glass, or playing catch would become unpredictable gambles, governed by uncertainty and caprice. Society itself would struggle to function as the once stable laws that kept the world in order crumbled like sand slipping through fingers. But thankfully, that is not the world we live in. No matter where you are on this planet or beyond it, gravity remains faithful to its ancient promise. Whether you drop a pen on a bustling street in Tokyo, a coin in the vibrant markets of Cape Town, or a feather on the silent, dusty plains of the moon, gravity treats them all the same. It shows no partiality or hesitation. The objects fall with equal grace and precision, regardless of their weight, shape, or material composition. This remarkable uniformity is known as the universality of free fall. It is so deceptively simple and steadfast that we often take it for granted, rarely pausing to marvel at just how astonishing it truly is. Consider this: a heavy bowling ball and a fragile, crumpled piece of paper dropped simultaneously in a vacuum will hit the ground at precisely the same time. This is not because their masses are equal or because air resistance has been neutralized, but because gravity itself is indifferent to such distinctions. This perfect indifference is no mere coincidence. It stands as one of the most sacred and profound symmetries known to physics. Yet despite its central role in our understanding of the cosmos, we still lack a fundamental explanation for why this happens. Why does gravity, alone among nature's forces, treat every object as an equal player on its cosmic stage? The story begins centuries ago with the legendary Galileo Galilei, who is often credited with first challenging the ancient Aristotelian belief that heavier objects fall faster than lighter ones. According to folklore, Galileo's experiments, dropping balls of different weights from the Leaning Tower of Pisa, showed that their rate of fall was the same. Although the accuracy of this particular tale is debated, the principle it illustrates remains a cornerstone of physics. Later, Albert Einstein brought the universality of free fall to new heights by weaving it into his groundbreaking theory of general relativity. In Einstein's vision, gravity is no longer a conventional force pulling objects toward each other, but rather a manifestation of curved space-time geometry. Massive objects bend the fabric of space and time, creating invisible pathways, geodesics, that all matter, regardless of its nature, must follow. In this elegant framework, the universality of free fall emerges naturally. All objects traverse the same curved trajectories, blurring the line between their individual identities. There is a beautiful poetry in this idea. It suggests that the universe, in its infinite complexity, gently guides all things, rocks, rivers, humans, machines, along equal and harmonious paths. It erases the distinctions between gold and stone, between the mechanical and the organic, and reveals a hidden unity beneath apparent diversity. But the beauty conceals a deep and persistent mystery, because despite the countless experiments conducted over centuries, in laboratories high above Earth's atmosphere, and even in space, this principle remains a stubborn puzzle. The equivalence principle, as it is often called, has been tested with extraordinary precision. Still, we have yet to uncover a deeper reason why gravity should be so perfectly fair. Contrast this with other fundamental forces of nature. Electricity, for example, shows distinct behaviors based on the charge of particles. Magnetism depends on polarity, and the strong and weak nuclear forces have their own complex rules dictating interactions at the subatomic level. These forces discriminate, they differentiate, they select. Gravity, by comparison, stands out in its patient, silent impartiality. It treats the majestic toll of a cathedral bell and the gentle drift of a snowflake alike, without bias, without exception. Scientists have not taken this universal fairness for granted. They have sought tirelessly to find cracks in the facade, to detect even the tiniest deviation that might shatter the illusion. They have launched satellites specifically designed to measure the free fall of test masses in orbit with unprecedented accuracy. They have studied whether different atomic isotopes respond uniquely to gravity. Time and again, the results reaffirm the perfect consistency of free fall. This unyielding equality is so fundamental that if even one particle or object failed, the test, entire pillars of modern physics, Einstein's relativity, the standard model of particle physics, and beyond, would be thrown into question. Yet despite this unwavering reliability, the universality of freefall stands at odds with the world of the very small. The quantum realm is chaotic, jittery, ruled by uncertainty and probability. Particles flicker in and out of existence, positions and velocities blur, and determinism gives way to waves of possibility. How can such a turbulent, microscopic dance give rise to the clean, orderly behavior of equal falling? This contradiction signals a profound clash, the ongoing battle to reconcile quantum mechanics with general relativity. Some physicists believe the answer lies where these two great theories collide. Perhaps the secret to gravity's perfect fairness, and the key to a grand unified theory of everything, resides in the unexplored frontier between the very large and the very small. Others entertain the possibility of hidden influences, subtle forces or principles yet to be discovered, that preserve this cosmic balance without revealing their presence outright. There are proposals that gravity itself might be an emergent phenomenon, not a fundamental force, but a manifestation of deeper information theoretic or thermodynamic laws governing the universe. Maybe gravity arises from entropy, from the quantum entanglement of space-time itself, or from the fundamental logic encoded in the fabric of reality. These ideas, though still speculative, offer tantalizing glimpses into a cosmos far stranger and more beautiful than classical physics ever imagined. Whatever the ultimate explanation, the answer remains elusive, just beyond the edge of our current understanding. And perhaps that is part of the profound wonder of gravity's universality. Every time an object falls, whether it's a meteor blazing through Earth's atmosphere or the silent tears of a grieving soul, the universe performs an ancient and sacred ritual. It quietly acknowledges that some laws are so deeply woven into the essence of existence that they defy full comprehension. Free fall, then, is far more than a simple motion under a force. It is the universe whispering across time and space. No matter your size, your shape, your story, you are part of something infinitely greater. You are not alone in your descent through the cosmos. And maybe, just maybe, that knowledge is enough to inspire awe, humility, and connection. Why do quarks have fractional charges? No explanation. Imagine stepping into a grand hall of mirrors, each reflection twisting and splitting endlessly, revealing facets of reality you didn't expect to see. Now imagine that within this hall, the tiniest building blocks of matter, the quarks, carry charges that are not whole, not neat, but fractional. Unlike the electrons you've heard about, which hold a single, neat negative charge, quarks defy that simplicity. They carry charges, like 1/3 or 2/3 of a fundamental unit. This fractional charge is one of the most perplexing features of the quantum world, a mystery that physics has observed but never truly explained. Why do quarks have fractional charges? The question sounds simple, but it cuts to the very core of what it means to be fundamental, to be indivisible, to be real. To understand this strangeness, you first need to know what a charge really is. Charge is a property that governs how particles interact via electromagnetic forces. It's why magnets stick to refrigerators, why lightning strikes the tallest tree, and why your phone lights up when you touch the screen. The electron's charge is the standard candle, -1 in units we use. Everything else is measured relative to it. Protons carry a positive charge equal in magnitude to the electron's negative charge. It's tidy. It fits neatly into the puzzle of atoms and molecules. But quarks, well, they break the mold. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Each flavor carries a charge that's a fraction of the electron's charge, either +2, 3 or 1 to 3. This means if you took 3 quarks and combined them just right, their charges add up to a whole number, forming particles like protons and neutrons, which have charges +1 and 0, respectively. It's as if quarks are secret agents of fractional power, always working together to create the familiar whole world we perceive. But why fractions? Why not whole charges? Why this precise arithmetic? The answer, at least the answer physics currently offers, is we don't really know. The Standard Model, our best description of particle physics, takes these fractional charges as a given. They're built into the theory's mathematical framework, an intrinsic part of the quark's identity. The theory explains how quarks interact, how they combine, and how forces act upon them, but it does not provide a deeper reason for the existence of fractional charges. It's a bit like accepting the rules of chess without knowing why the bishop moves diagonally or why the queen can traverse the board freely. The rules work perfectly, they produce a coherent and predictive game, but their origins remain mysterious. Some physicists have searched for hidden symmetries or more fundamental structures beneath the Standard Model, attempting to find a reason why fractional charges arise. Grand unified theories, string theory, and other speculative frameworks suggest that what we see as fractional charges might emerge from more complex geometry, from higher dimensions curled tightly beyond our perception, or from the way fundamental strings vibrate. But these remain speculative, mathematical dreams awaiting experimental confirmation. What makes the mystery deeper is the fact that free quarks alone, have never been observed. Unlike electrons, which roam freely, quarks are forever trapped inside larger particles, bound together by the strong force. This phenomenon, called color confinement, means quarks are always hidden from direct view, and we infer their properties only from the particles they compose. So we measure fractional charges not on isolated quarks, but on their collective effects. It's as if quarks are secret players behind a curtain, never stepping fully into the spotlight. Moreover, the fractional charges of quarks obey a delicate balance, without which matter as we know it would not exist. This precise balancing act ensures that protons carry a +1 charge, neutrons 0, and atoms maintain electrical neutrality. It's a cosmic choreography with no apparent director. The fractions add up perfectly, and the universe builds complexity on top of these fractions. Yet the question lingers with an almost haunting persistence. Why these fractions? Why these particular fractions? Why does nature pick such strange, non-integer values to govern the most fundamental pieces of matter? Could it be that these fractions are windows into deeper truths, clues left for us to decipher? Or are they simply arbitrary values handed down by the universe without explanation? The honest answer is that we don't know. It's one of those fundamental facts that we accept because it works, because the math demands it, because experiments consistently show it, but the deeper why remains elusive. It sits like a shadow on the foundation of physics, a question without an answer, a riddle that might require a revolution in our understanding to solve. Some have tried to find meaning in patterns, searching for relationships between these fractions and other fundamental constants of nature. Others have speculated that the fractions might arise from the topology of space-time itself, or from symmetries that only reveal themselves at energy scales far beyond our current reach. Yet all these theories remain tentative. They paint fascinating pictures, but stop short of definitive proof. Perhaps this mystery is a reminder that even in a universe described by elegant equations and predictable laws, there remain pockets of profound uncertainty. The fractional charges of quarks are a whisper that nature still holds secrets, that the fundamental fabric of reality is woven with threads we have yet to fully unravel. They challenge us to keep asking, keep probing, keep imagining beyond the limits of our current knowledge. And maybe, just maybe, the fractions are the clues, not just to the makeup of matter, but to the nature of reality itself. The universe doesn't always give us whole numbers or simple answers. Sometimes it invites us to embrace the complexity, to marvel at the partial, the fractional, the mysterious. And in that invitation lies the true beauty of physics, an endless journey toward understanding the unknown, where every answer opens the door to 1,000 more questions. Does the universe rotate? No proof, but some patterns suggest it. Have you ever stood in the middle of a field at night, looked up at the sky and wondered whether the stars themselves might be spinning? Not just around galaxies, not just orbiting other stars, but in one great cosmic pirouette. It's an absurd question at first. After all, rotate with respect to what? Space has no outer walls, no ceiling to pin a compass on. There's no absolute reference point in the void against which the entire universe could be measured for spin. And yet, certain patterns in the cosmic microwave background, the afterglow of the Big Bang, suggest a faint echo of rotation, as if the universe itself, from its earliest moments, had a preferred direction, a subtle spiral woven into its structure. It's like finding brushstrokes in a painting you thought was created by random splashes. This isn't a fringe idea. It's a question that stretches the very foundations of cosmology. Could the entirety of space and time be twisting ever so, slightly around an unseen axis? And if so, what would that mean for everything we think we know? To understand the strangeness of this possibility, we have to remember that everything rotates. Planets spin, stars rotate, galaxies whirl like vast cosmic hurricanes. Even black holes twist space-time into loops and whirls. Angular momentum is one of the most universal properties in physics. Nothing escapes it. So why should the universe as a whole be the one exception? General relativity, our best theory of gravity, technically allows for a rotating universe. In 1949, Kurt Gödel, yes, the same Gödel famous for his incompleteness theorems, found a solution to Einstein's field equations that described a universe rotating on its axis. It was a bizarre construct. Time loops were possible, and causality became a soft rule rather than an absolute law. You could, in theory, travel into your own past. Most physicists dismissed it as a mathematical curiosity, but the fact that Einstein's own equations didn't forbid it left a lingering question. What if rotation is real, just too subtle for us to perceive? Enter the cosmic microwave background, the oldest light in the universe, a whisper from when everything was still fire and fog. Scientists studying its faint irregularities have found hints of asymmetries, of alignments that shouldn't be there. They call it the axis of evil, a strange term for a strange idea. This alignment suggests that there might be a preferred direction in the cosmos, which flies in the face of the cosmological principle. The assumption that the universe is isotropic and homogeneous on large scales. If this axis holds up under scrutiny, it could be the fingerprint of a slow, ancient rotation. Not enough to make galaxies spin in unison, but enough to bend the canvas of space-time ever so slightly, just enough to matter. But here's the dilemma. If the universe were rotating, we'd expect to see certain effects. Frame dragging on a cosmic scale, shifts in the polarization of light, perhaps even spiraling patterns in the distribution of galaxies, and yet we don't. At least, not clearly. The patterns we do see could just be statistical flukes, noise masquerading as meaning. The Planck satellite, the most precise observer of the cosmic microwave background, gave us data that both intrigued and confused cosmologists. Some saw the axis, others didn't. The question became not just whether the universe rotates, but whether our instruments and biases were creating the illusion of spin. Could our position in the universe, our particular galactic neighborhood, be skewing our perception of the cosmic backdrop? Could the shape of the universe itself be playing tricks on us, its curvature, its boundaries, its topology? These aren't just technical questions. They cut to the heart of how we understand the cosmos. If the universe rotates, even a little, it suggests that there is structure to the universe beyond what we currently see. It implies a before and an after, a directionality, a broken symmetry in the most sacred assumption of modern cosmology. It suggests that the universe might not be a passive stage, but an active participant in the play. And what if it does spin? What then? Would it mean that the laws of physics are different in different directions? That time flows differently depending on your orientation in space. Would it affect how galaxies form, how stars ignite, how life evolves. These aren't hypothetical questions. They would force us to rewrite the very equations that govern our understanding of space, time, and causality. It might mean that the universe has a kind of memory, a built-in angular momentum from its birth that still echoes in its vastness today. And maybe, just maybe, it could point toward a deeper theory, one that includes rotation as a fundamental feature of reality, rather than an afterthought. Some physicists speculate that if the early universe was spinning, that spin could have seeded the structures we see today. Without it, perhaps galaxies wouldn't have formed. Perhaps stars would never have ignited. Perhaps we would not exist. That's the strange irony. A universe spinning in silence might have given rise to all the noise we call life. In the end, the question of whether the universe rotates remains unanswered, but not because it's meaningless, because it's profound. It forces us to ask what it would even mean for everything to spin. It reminds us that the universe is not just a collection of objects, but a whole, an entity that might have its own dynamics, its own motion, its own story. Perhaps we are passengers in a grand, slow-turning wheel, oblivious to the movement, because we are part of it. Like fish in a swirling ocean that don't realize the current is moving them. Or maybe, in the ultimate cosmic joke, the universe does rotate, but only in ways we can never detect, hidden behind the veil of symmetry, protected by the limits of our perspective. Either way, the idea lingers that even the cosmos might not be still, that even the stars above us might be dancing to a rhythm older than time itself. And in that possibility, we find both humility and wonder, because sometimes not knowing is the beginning of a deeper kind of knowledge, the kind that turns silence into a question, and questions into the seeds of discovery. Why is there only one time dimension and three space? What if I told you that the very fabric of your life, the forward flow of time you take for granted, the three-dimensional space you navigate daily, was not only strange, but possibly one of the biggest unsolved riddles in existence? Imagine waking up in a world where time split into two branches, where you could move left and right in one timeline, but also up and down in another. Picture a realm where instead of one ticking clock pulling everything toward the future, there were multiple temporal threads, tangled like a cosmic braid. Sounds absurd, even terrifying. And yet the only thing stopping that from being real is we don't know. Physics tells us that we live in a universe with three spatial dimensions: length, width, and height, and one dimension of time. This setup feels natural to us because it's all we've ever known. But there is no deep reason, no mathematical necessity, no logical rule that demands this specific configuration. And that's the problem. Because when something is so foundational, so inescapably woven into reality, but defies explanation, it becomes a cosmic clue, like a silent fingerprint left by something deeper, something we haven't yet understood. So why three space and one time? Why not four space and zero time? Or two time and two space? In theory, all are mathematically possible. But our universe chose this combination: three dimensions where you can move freely, and one that drags you forward whether you like it or not. The imbalance feels deliberate, but we have no idea who or what made the choice. Let's start with the spatial side. In 3 dimensions, you can define position with just 3 coordinates. This is not arbitrary. It allows for stable planetary orbits, complex biological structures, and even the very atoms that form you. If space had 4 or more dimensions, gravity would weaken too quickly with distance, and stable systems, like stars and planets, might not exist. The forces that hold galaxies together would lose their grip, and the delicate balance that enables planets to revolve around stars in predictable patterns would dissolve. Life as we know it, with its intricate molecular machinery, would never have a chance to arise. In lower dimensions, everything becomes too flat, too simple to allow the emergence of life. The richness of textures, the depth of form, the complexity of interactions, all depend on having enough dimensions to move twist, and grow. But even this explanation feels like retrofitting, like nature made a choice and we're trying to justify it afterward. Now think about time. It's a single arrow, pulling everything along a one-way track from past to future. You can't pause it. You can't rewind it. You can't sidestep it. This is wildly different from space. In space, you can walk back and forth. You can look around. But time traps you. It doesn't just flow, it flows in one direction. Why? Physics doesn't truly answer this. Equations describing motion, gravity, and quantum mechanics all work, the same whether time moves forward or backward. The fundamental laws themselves are time-symmetric, yet our experience is anything but. So why don't we experience both? Why can't we remember the future? Why is the past fixed, but the future open? Some say entropy is the culprit, that the arrow of time emerges from the universe starting in a highly ordered state and moving toward disorder. But this isn't a true cause. It's a consequence. Entropy explains the direction of time, but not why there is only one dimension of time instead of two or more. It tells us that disorder tends to increase, but it doesn't explain why time itself is linear, singular, relentless. If we imagine a universe with two time dimensions, bizarre things happen. Causality breaks down. Events can loop or occur in paradoxical sequences. The rules of logic fray at the edges. In such a universe, cause and effect lose their clarity. Past and future become tangled in a confusing dance. Predictability, a foundation of science, would evaporate, and yet mathematically it's not impossible, it's just unstable. Like a stack of cards that topples under its own potential, a universe with multiple times might simply collapse or fail to sustain complexity for long. The universe we have, 3 space, 1 time, turns out to be the minimal setup that still allows complexity, consciousness, and continuity. This precise balancing act is a cosmic miracle. It's a sweet spot in the vast landscape of mathematical possibilities. But again, this is observation, not explanation. It's like being handed a perfectly tuned violin and being told it just works. You might learn to play it, you might even understand its mechanics, but you still won't know who made it sing. Some theorists have ventured beyond the known, proposing multiverses where different numbers of dimensions play out in infinite variations. In some of those worlds, time might not exist at all. Or it might exist as a landscape, with past, present, and future visible like distant mountains. In others, time might be cyclical, folding over itself like a looped melody, endlessly repeating, allowing realities to rewind and replay. Such concepts challenge our deepest intuitions, but open doors to profound possibilities. In this universe, however, you are shackled to a single moment, riding the wave of a solitary temporal direction you cannot control. And maybe that's not a flaw. Maybe that's the design. Because with 3 dimensions of space, you have freedom. You can build, explore, move. But with only 1 dimension of time, you have urgency. You must act. You must choose. You must live forward. The imbalance forces story. It demands purpose. Without it, there would be no meaning, only static existence. So perhaps this strange asymmetric configuration, 3 spaces, 1 time, isn't just a mathematical quirk. Perhaps it's the stage upon which consciousness becomes possible, where memory forms, where decisions matter, where reality unfolds not as a frozen equation, but as a lived experience. And as you move forward through that lone river of time, carving your path through the open space of existence, you carry within you the greatest mystery of all. Not just why this universe is the way it is, but how you, a temporary traveler in its structure, are able to wonder about it at all. You are not merely drifting on the currents of time and space. You are the universe reflecting on itself, questioning the grand design, searching for meaning in the very fabric that sustains you. This mystery, the imbalance of dimensions, The arrow of time, the shape of space, remains one of the deepest puzzles facing modern physics and philosophy. It challenges us to rethink our assumptions, to look beyond the comfortable frameworks, and to embrace the possibility that the universe is far stranger, more intricate, and more wondrous than our current understanding allows. And maybe that's the true gift of this cosmic question. Not an answer, but an invitation. An invitation to keep exploring, keep imagining, keep dreaming. To be humble in the face of mystery, yet bold enough to seek its light. For in the dance of three spaces and one time lies the very essence of existence. And within that dance, the spark of your own consciousness, lighting the path forward into the unknown. The vacuum catastrophe. Quantum field theory predicts infinite vacuum energy. Imagine you're sitting alone in a completely silent room. The air is still. The lights are off. Your breathing is soft and every sound has vanished. You feel like you've reached a state of perfect stillness, like the universe for a moment is truly at rest. But what if I told you that even in that silence, even in the deepest, darkest vacuum of space, where no particles are supposed to exist, the cosmos is anything but calm? That underneath the emptiness, beneath the apparent nothing, there is a violent storm of invisible energy, seething, fluctuating, churning with the raw potential of creation and destruction. This is the paradox of the vacuum. And the story that follows, one that few truly understand, is not just the strangest whisper of quantum physics. It's a catastrophic contradiction so large, it threatens to unravel our understanding of reality itself. This is the tale of the vacuum catastrophe. In classical physics, a vacuum is simple. It's empty. A perfect void, devoid of matter, motion, and energy. A place where nothing happens. A blank canvas, a cosmic void. This concept seems intuitive. If there's no matter, no particles, no light, then there should be no activity, no energy, no influence. It's an idea that shaped centuries of scientific thought, deeply ingrained in how we imagine space. The great philosophers and physicists of the past assumed the vacuum was a passive backdrop, a neutral emptiness waiting to be filled. Newton pictured space as an invisible stage where forces and particles played their parts, but never as an actor itself. Even Einstein, with his revolutionary views on space-time, treated the vacuum as a sort of malleable stage, but still a stage nonetheless. But quantum field theory, the cornerstone of modern particle physics, paints a drastically different picture. According to it, even the emptiest part of the universe is not truly empty. It's alive with activity. Fields permeate all of space, and even when there's no particle present, those fields fluctuate constantly due to the uncertainty principle. In quantum terms, nothing is unstable. These fluctuations mean that particles and antiparticles can pop into and out of existence momentarily. Virtual particles blinking into the void for just a moment before vanishing again. This phenomenon is not just theoretical musing. It's a mathematically mandated consequence of the laws of quantum mechanics. The vacuum itself buzzes with ephemeral energy, an ocean of possibility underlying everything we perceive. This leads to the notion that even the vacuum contains energy, a non-zero ground state known as vacuum energy. And when physicists tried to calculate how much energy should be present in empty space, the numbers they got were not just large, they were monstrous. According to quantum field theory, the vacuum energy density should be about 10 to the 120 times higher than what we observe. That's a number so large, it defies comprehension. To put it in perspective, if that energy truly existed in space, the gravitational force it would create would rip the universe apart in an instant. Galaxies would never form. Stars couldn't coalesce. The expansion of the universe would be so rapid, so violent, that nothing we know could exist. The cosmic fabric would be torn asunder, unable to sustain any structure, any matter, any life. But that's not what we see. Instead, when astronomers measure the actual energy density of the vacuum through the effects of dark energy on cosmic expansion, they find something incredibly tiny, trillions upon trillions upon trillions of times smaller than theory predicts. This is the vacuum catastrophe, the single largest mismatch between theory and observation in the history of science. 100 orders of magnitude off. It's as if you calculated the height of a building and were off by the distance from Earth to another galaxy. That's not just wrong, that's a universe-breaking kind of wrong. And the worst part, we have no idea why. All our equations work. Quantum electrodynamics, quantum chromodynamics, the Standard Model, all are stunningly accurate in every experiment we've thrown at them. But when it comes to the vacuum, they predict a doomsday energy density that simply isn't there. It's like having a perfectly constructed machine that functions flawlessly, except for one critical gauge that reads impossibly high values no one can explain. The vacuum energy predicted is a kind of silent storm brewing beneath reality, yet reality itself remains calm and hospitable. So how do we make sense of this? One possibility is that our understanding of gravity, particularly how it interacts with quantum energy, is incomplete. Gravity, described by Einstein's general relativity, operates on scales vastly different from quantum fields. The marriage between the quantum world and gravity is notoriously difficult. Perhaps gravity somehow cancels out most of the vacuum energy, or only sees a portion of it. Maybe there are unknown mechanisms or symmetries that fine-tune this energy to near zero, preventing catastrophic cosmic destruction. But so far, these remain speculative ideas without experimental confirmation. Another idea is that the vacuum energy is real, but balanced out by a cosmological constant with the opposite sign, a sort of mathematical sleight of hand to cancel infinity. This cosmological constant was introduced by Einstein himself as a fudge factor to allow a static universe, which he later called his greatest blunder after the discovery of cosmic expansion. Yet now, this constant seems to embody the mysterious dark energy driving the accelerated expansion of the universe. The near-perfect cancellation between vacuum energy and cosmological constant remains a puzzling coincidence, a cosmic tuning that lacks an underlying reason. It's like tuning a cosmic piano by ear, elegant maybe, but deeply unsatisfying, because no underlying reason explains why the numbers cancel out so precisely. It's like throwing random numbers into a blender and having the result come out exactly zero. This fine-tuning is unnerving, suggesting that some hidden principle or unknown physics is at play. The universe appears to be whispering a secret, but we have yet to decode its language. Some have proposed that perhaps we live in a multiverse, a vast collection of universes, each with different vacuum energies. Most are too chaotic to support life, but ours, by chance, just happens to fall within the tiny sliver of possibilities where things are calm enough for complexity to form. In this view, we exist not because the vacuum is the way it is, but because in universes where the vacuum is any other way, we wouldn't be here to ask about it. It's a clever answer, but not a satisfying one, because it replaces understanding with probability. It says, this just happened to work out. And deep down, that's not what we seek. We want to know why. We want to know why the universe, when stripped down to its emptiest form, still pulses with energy, and yet does so in a way that permits galaxies, minds, and meaning. We want to understand why the vacuum isn't just an absence but a presence. Why the void is not silent but hums with potential. Why the cosmos is, in a very real sense, alive with a restless energy that defies our simplest expectations. In our quest to unify quantum mechanics and gravity, the vacuum catastrophe sits like a dragon in the cave, massive, dangerous, and impossible to ignore. Every attempt to build a theory of everything must confront it. String theory, loop quantum gravity, emergent spacetime, all must reckon with this invisible ocean of power humming beneath the void. Until we do, the vacuum will remain our greatest contradiction, the place where nothing exists, yet everything begins, and perhaps, just perhaps, hidden in that paradox lies the key to the next great revolution in science. Because sometimes, the biggest secrets are buried not in what we see, but in what we assume to be empty.